Hey there, cosmic explorers. Welcome back to my channel, where we dive into the biggest mysteries of the universe. And today's enigma is out of this world. Imagine a visitor from another star system zipping through our solar system, defying expectations and sparking debates. Is it a mundane comet or something far more extraordinary? Meet 3I Atlas, the third known interstellar object to grace our celestial neighborhood, and the subject of our most thrilling video yet. Discovered in 2025 by the Atlas telescope in Chile. 3I Atlas isn't your average cosmic rock. This fast-moving interloper is hurtling through space at 58 kilometers per second on a hyperbolic trajectory that'll fling it back into the depths of the galaxy. But here's the kicker. Its odd behavior, like a sun-facing plume and a bizarre chemical makeup, has scientists and enthusiasts alike wondering, could this be evidence of alien technology? Or is it just a comet with a wild personality? In this video, we break down the science behind 3I Atlas's mind-bending journey. We'll trace its origins to the direction of Sagittarius, decode its icy chemistry using cutting-edge telescopes like JWST, and explore why its trajectory has some experts whispering about extraterrestrial possibilities. Along the way, we'll unpack hyperbolic orbits, galactic recycling theories, and even imagine what it'd take to launch a mission to catch up with this cosmic speedster. Whether you're a seasoned space buff or just curious about what's out there, this video will take you on a journey through physics, chemistry, and the thin line between science and speculation. Could 3I Atlas be a message in a bottle from another civilization, or is it simply a reminder of how much we still have to learn about our universe? Let's find out. Hit that subscribe button if you're ready to explore the cosmos with us, and smash the like if you think 3I Atlas might just be hiding secrets we've yet to uncover. Stay curious, and let's dive into the paradox that's turning heads across the scientific community. In the vast, silent expanse of the cosmos, where stars burn like distant lanterns and galaxies spiral in eternal dance, a solitary traveler emerged from the unknown. 3I Atlas, a name now etched into the annals of astronomy, arrived in our solar system like a whisper from the depths of interstellar space, defying the familiar laws that bind celestial bodies to their stellar cradles. Discovered in 2025, this enigmatic object challenged humanity's understanding of cosmic phenomena, sparking a cascade of questions that ripple across disciplines. What force hurled it from the void? What secrets does its composition hold about the birth of stars and planets in distant corners of the Milky Way? And most tantalizingly, could it be a harbinger of something far stranger than a mere comet? The discovery of 3I Atlas was not a sudden revelation, but a slow, methodical unraveling of its identity. Initially mistaken for a rogue asteroid or a misaligned planet, its true nature revealed itself through the relentless scrutiny of Earth's observatories. The Asteroid Terrestrial Impact Last Alert System, ATLAS, designed to guard against potential threats to our planet, first spotted the object on 1 July 2025. Yet, as the data accumulated, it became clear that 3I Atlas was not merely passing through, it was a visitor from another star system, a relic of cosmic chaos that had traveled billions of kilometers to cross paths with our own. Its trajectory, a hyperbolic arc unshackled from the sun's gravitational embrace, marked it as the third confirmed interstellar object to traverse the solar system, joining the ranks of 1I Oumuamua and 2I Borisov. But unlike its predecessors, 3I Atlas carried with it a wealth of mysteries that demanded answers. At the heart of 3I Atlas's significance lies its trajectory, a path that defies the circular or elliptical orbits typical of solar system objects. Hyperbolic trajectories, characterized by an orbital eccentricity exceeding 1,000, signify that an object possesses enough kinetic energy to escape the gravitational influence of its host star. For 3I Atlas, this escape velocity is staggering: 58 kilometers per second, 36 miles per second, nearly double the speed of the previous interstellar interloper, 2I Borisov. Such a velocity ensures that the comet will not linger in the solar system, but will instead vanish into the interstellar abyss after its closest approach to the Sun on 29 October 2025. This trajectory is not arbitrary, but a consequence of the comet's origin. Calculations tracing 3I Atlas's path backward through space reveal that it entered the solar system from the direction of the constellation Sagittarius, near the heart of the Milky Way. Here, the gravitational interactions between stars and the dense clouds of gas and dust in the galactic core likely played a role in shaping its journey. The comet's velocity components suggest it belongs to the thick disk population of the galaxy, a region populated by ancient stars with lower metallicities, hinting at an age potentially exceeding 7 billion years. This places 3I Atlas in a category of cosmic relics predating the solar system itself, offering a unique window into the primordial conditions of the galaxy. Yet the comet's journey is not solely defined by its origin and trajectory. Its physical characteristics, its coma of gas and dust, its composition, and its activity paint a picture of a body transformed by its encounter with the Sun. Unlike the inert, asteroid-like 1I Oumuamua, 3I Atlas is a dynamic world, its icy nucleus sublimating under the Sun's heat to produce a glowing halo of material. Observations by the Hubble Space Telescope and the James Webb Space Telescope, JWST, have revealed a coma rich in carbon dioxide, water ice and carbon monoxide, with traces of cyanide and atomic nickel. These findings not only confirm its classification as a comet, but also provide clues about its formation history. The abundance of carbon dioxide, in particular, suggests that 3I Atlas formed far from its parent star, beyond the CO2 frost line, where temperatures are cold enough for the gas to condense into ice. This places it in stark contrast to most solar system comets, which originate from the Kuiper belt, or the Oort cloud, and are primarily composed of water ice. The arrival of 3I Atlas is more than a fleeting astronomical event. It is a profound opportunity to study the chemistry and dynamics of an alien world. Every molecule detected in its coma, every particle of dust ejected from its nucleus, carries the imprint of a star system billions of years removed from our own. The presence of carbon dioxide in such high concentrations challenges existing models of cometary evolution, suggesting that the comet's parent star may have formed in a different galactic environment, one where the balance of volatiles differs from the solar system's. Furthermore, the detection of heavy isotopes like carbon-13 in CO2 hints at processes of stellar nucleosynthesis and interstellar enrichment that may have occurred in the comet's home system. Beyond its composition, 3I Atlas's trajectory and timing raise intriguing questions about the frequency of interstellar visitors. If such objects are common, they could serve as cosmic messengers, carrying material from one planetary system to another. Theoretical models predict that gravitational interactions between stars in dense regions of the galaxy, such as the galactic center or globular clusters, could eject comets and asteroids at velocities sufficient to escape their native systems. Over billions of years, these objects would drift through the galaxy, occasionally crossing the paths of other stars. The fact that 3I Atlas was discovered in 2025 suggests that our technological capabilities are finally catching up to the scale of these phenomena. Future surveys, such as those conducted by the Vera C. Rubin Observatory, promise to uncover even more interstellar travelers, painting a fuller picture of the galaxy's dynamic exchange of matter. Yet perhaps the most profound implication of 3I Atlas lies in its age. If the comet is indeed older than the solar system, it predates the formation of Earth and the emergence of life. In this context, 3I Atlas becomes a temporal bridge, a fragment of the galaxy's ancient past that now traverses the future. Its passage through the solar system is not merely a scientific curiosity, but a reminder of the interconnectedness of all things in the cosmos. The materials that forged the stars and planets of its birthplace may now interact with the chemistry of our own, raising the possibility that interstellar comets could contribute to the building blocks of life elsewhere in the galaxy. As 3I Atlas hurtles toward perihelion, its journey through the solar system continues to unfold. The hyperbolic trajectory that defines its existence is not just a mathematical abstraction, but a testament to the cosmic forces that govern the movements of celestial bodies. To fully grasp the significance of this interstellar visitor, we must delve deeper into the physics that shapes its path. How does the Sun's gravity influence its motion? What role do the planets play in its passage? And what can its trajectory reveal about the origins of interstellar objects? These questions form the foundation of the next segment, where we will explore the mechanics of 3I Atlas's voyage and the scientific tools that allow us to track its every step. In the vast, silent expanse of the cosmos, objects move under the invisible hand of gravity, their paths etched by the delicate balance between kinetic energy and gravitational pull. Most celestial bodies, planets, moons, and even distant asteroids are bound to their host stars in elliptical orbits, tethered by the gravitational embrace of their systems. Yet there exists a rare class of wanderers that defy this cosmic order: interstellar objects like 3I Atlas, which traverse the galaxy with trajectories so extreme they never return. To understand 3I Atlas's fate, we must first grasp the physics of escape velocity, the threshold at which an object breaks free from a star's gravitational grip. Imagine a stone tossed into the air. If thrown gently, it arcs back to Earth. If hurled with sufficient force, it escapes entirely. The same principle governs 3I Atlas. Its hyperbolic trajectory, a mathematical curve that opens infinitely, is not a mere quirk of nature, but a testament to its origins beyond our solar system. Unlike the familiar ellipses of planetary orbits, a hyperbola represents a path of perpetual departure, a cosmic arrow aimed at the void. This trajectory, dictated by its velocity and the sun's gravity, reveals a story of acceleration, ejection, and interstellar drift. The key to unlocking 3I Atlas's fate lies in orbital mechanics, a field that quantifies the dance of celestial bodies. Every object in the solar system possesses a velocity relative to the sun, and the nature of its path depends on whether this velocity exceeds the sun's escape velocity. For an object to escape the solar system, it must achieve a hyperbolic excess velocity, VF10, that overcomes the sun's gravitational influence. 3I Atlas arrives with VF10 of 58 kilometers per second, over twice the speed of the previous interstellar visitor, 2I Borisov. This velocity is not arbitrary. It is the product of gravitational interactions in its home system, where unseen forces flung it into the interstellar abyss. The shape of a trajectory is defined by its orbital eccentricity, E, a dimensionless number that describes the deviation from a perfect circle. Circular orbits have E0, while elliptical orbits range from E0 to E1. Ampere's parabolic trajectory, E1, marks the boundary between bound and unbound motion, and a hyperbolic path, E, signifies an object that will never return. 3I Atlas's eccentricity of 6.141 is staggering, transforming its orbit into a nearly straight line. From a vantage point in the solar system, it appears to slice through space like a blade, unimpeded by the sun's gravity. This extreme eccentricity is not merely a mathematical curiosity. It is a fingerprint of interstellar provenance. The higher the eccentricity, the more certain it is that an object does not belong to the solar system. 3I Atlas's trajectory, calculated using precise measurements of its position and velocity, places it firmly in the category of interstellar rogues. Unlike asteroids or comets born in the Kuiper belt or Oort cloud, which follow bound paths, 3I Atlas has no home to return to. Its journey is one way, a lonely voyage through the galaxy. The existence of hyperbolic trajectories like 3I Atlas's raises profound questions about the dynamics of interstellar space. Such paths are not random. They are the result of gravitational slingshots or violent encounters in distant star systems. In the cradle of its birth, 3I Atlas may have once orbited a star, perturbed by the gravitational dance of planets or passing stars. Ampere's close encounter with a massive planet could have accelerated it to escape velocity, hurling it into the void. Alternatively, the chaotic birth of a star system where protostars collide or compete for material might have expelled 3I Atlas into the interstellar medium. These mechanisms hint at a galaxy teeming with transient travelers. While 3I Atlas is the third confirmed interstellar object, it is likely one of countless others. Each hyperbolic trajectory is a clue to the gravitational history of its origin, a relic of a system long since transformed. The fact that 3I Atlas's path is aligned with the ecliptic, the plane of the solar system's planets, is particularly intriguing. Though statistically rare, this alignment suggests that interstellar objects may not be uniformly distributed, but influenced by the gravitational architecture of the Milky Way. Moreover, the study of hyperbolic trajectories informs our understanding of the solar system's boundaries. 3I Atlas's closest approach to the Sun, 1.36 AU, places it between the orbits of Earth and Mars, yet its path ensures it will never threaten our planet. Its hyperbolic excess velocity guarantees that it will exit the solar system by 2026, leaving no trace of its passage except in the data of telescopes and the minds of those who tracked its journey. This underscores the importance of global observational networks like ATLAS, ZTF, and JWST, which act as sentinels against cosmic strangers. Yet 3I Atlas's trajectory also highlights the limitations of human perception. For months before its discovery, it lingered in the dense star fields near the galactic center, its faint glow masked by the brilliance of the Milky Way. Only with the advent of advanced surveys and adaptive optics could its true nature be unveiled. This realization humbles us. The universe is vast, and our ability to observe it is limited. Perhaps other interstellar visitors, their hyperbolic paths undetected, have passed silently through the solar system, unseen and unrecorded. To trace 3I Atlas's origin, we must reverse the clock, following its hyperbolic path backward through time. Like a river flowing toward a source, its trajectory points to a distant birthplace in the Milky Way. But where exactly did it come from? The answer lies not in its speed alone, but in the subtle clues embedded in its motion, clues that reveal its age, its chemical heritage, and the star system that once held it. In the next segment, we will embark on a journey across the galactic plane, piecing together the cosmic map that leads us to 3I Atlas's home. In the vast, uncharted expanse of the cosmos, a silent traveler drifts through the vacuum of space. Discovered on 1 July 2025 by the asteroid terrestrial impact last alert system, Atlas, at Rio Hurtado, Chile, 3I Atlas is not merely another comet. It is a messenger from the depths of interstellar space, a relic of epochs long before the birth of our solar system. With a hyperbolic trajectory and a velocity exceeding 58 kilometers per second, this icy wanderer arrives not as a product of our cosmic neighborhood, but as a fragment of a distant stellar nursery, carried across the galactic currents by forces we are only beginning to comprehend. 3I Atlas is the third interstellar object confirmed to traverse our solar system, following the enigmatic 1I Oumuamua, NICE 2017, and the more recent 2I Borisov 2019. Yet, unlike its predecessors, 3I Atlas bears a unique signature, a coma rich in carbon dioxide, traces of water ice, and hints of complex organic molecules. Its arrival stirs questions about the universality of planetary systems, the chemistry of distant stars, and the shared heritage of comets across galaxies. As we trace its path, we are not merely observing a comet, we are decoding a cosmic story written in ice and light, spanning billions of years and countless star systems. This script invites you to journey alongside 3I Atlas, from its discovery to its closest approach to the Sun and beyond. Through the lens of science and imagination, we will unravel the mysteries of its origin, its fleeting passage through the solar system, and the profound implications it holds for our understanding of the universe. To grasp the nature of 3I Atlas, we must first understand the physics that govern its motion. The Sun's gravity is a powerful force, capable of binding planets, moons, and asteroids in elliptical orbits. Yet 3I Atlas defies this gravitational embrace. Its trajectory, defined by an orbital eccentricity of 6.141, a number far greater than the 1.0 threshold for hyperbolic paths, reveals that it is not bound to the solar system. Instead, it is a transient visitor, accelerated by the Sun's pull, but moving too swiftly to be captured. At its discovery, 3I Atlas was already hurtling through the inner solar system at 58 kilometers per second relative to the Sun, a speed nearly double that of 2I Borisov. This velocity, termed the hyperbolic excess velocity (MICHS), is the key to unlocking its origins. Unlike objects born within the solar system, which derive their energy from gravitational interactions with planets, 3I Atlas's speed suggests it has traveled independently through interstellar space for eons. By tracing its path backward in time, astronomers determined that it approached the solar system from the direction of the constellation Sagittarius, near the Milky Way's galactic center. What lies behind this trajectory? The answer lies in the comet's velocity components. Breaking down its motion into galactic coordinates, scientists identified a radial velocity, u, of near 51.0 kilometers per second, and a vertical velocity, watts, of puns 18.5 kilometers per second. These values place 3I Atlas in a category of stars and objects belonging to the Milky Way's thick disk, a spherical halo of older stars that predates the younger, flatter, thin disk, where our sun resides. Thick disk objects are relics of the galaxy's early history, their orbits tilted and chaotic compared to the orderly plane of the solar system. If 3I Atlas indeed hails from this ancient population, it could be 7 to 14 billion years old, older than the solar system itself. Such a timeline reshapes our perspective. If the comet has been traversing the galaxy for eons, it has likely encountered countless stars, nebulae, and gravitational tides that nudged it onto its present course. Its journey is not a single event, but a tapestry woven over millennia, punctuated by collisions, gravitational slingshots, and the quiet erosion of time. And now, for a brief moment, it intersects with our cosmic backyard, offering a glimpse into the primordial conditions of the Milky Way. As 3I Atlas draws closer to the Sun, its true nature begins to emerge. Telescopes on Earth and in space turn their gaze toward this interstellar wanderer, capturing snapshots of a world that may have never seen sunlight in the way we do. The Hubble Space Telescope reveals a fuzzy coma, a cloud of gas and dust encircling a nucleus shrouded in mystery. The James Webb Space Telescope JWST pierces through this veil, detecting carbon dioxide in abundance. Unlike any comet in our solar system, FEREX and ground-based observatories add further layers to the puzzle. Water ice, carbon monoxide, and even traces of cyanide and nickel vapor. The comet's coma is a dynamic phenomenon. As the sun warms its nucleus, volatile ices sublimate into gas, carrying dust particles into space. The result is a glowing envelope that stretches thousands of kilometers. Its reddish hue, a testament to the presence of large organic molecules. Observations suggest that 3I Atlas ejects 6 kilograms of small dust grains and 60 kilograms of larger particles every second, a rate comparable to the interstellar comet 2I Borisov, but modest compared to the Jupiter family comets of our own solar system. Yet the most striking feature of 3I Atlas is its chemical fingerprint. The JWST's spectrometer identifies a coma dominated by carbon dioxide, with a mixing ratio of CO2 to water 8 times higher than typical solar system comets. This anomaly raises questions. Did 3I Atlas form in a colder region of its parent star's protoplanetary disk, where CO2 could condense into ice? Or does its nucleus harbor a unique composition, shaped by the harsh radiation of interstellar space? Meanwhile, the detection of cyanide and nickel vapor adds another layer of intrigue. These elements, often linked to the breakdown of complex organics, hint at a history of exposure to cosmic rays and stellar winds. The absence of certain compounds, however, is equally telling. 3I Atlas is remarkably depleted in carbon chain molecules, like C2 and C3, substances commonly found in comets and asteroids. This scarcity suggests that the comet's chemistry diverges from the norms of our solar system, perhaps reflecting differences in the conditions of its birthplace. Could its parent star have formed in a denser, more turbulent region of the galaxy? Or did the comet's journey through interstellar space strip away volatile materials? Even its rotation tells a story. While the nucleus remains hidden beneath a dusty coma, subtle variations in brightness hint at a rotation period of approximately 16 hours. If confirmed, this would align with the irregular shapes typical of comets. But the gradual dimming of these variations over time suggests that the nucleus is becoming increasingly obscured by outgassing activity. Through these observations, 3I Atlas emerges not as an alien artifact, but as a natural, if extraordinary product of stellar evolution. Its journey is a testament to the resilience of matter across cosmic timescales, a reminder that the building blocks of life may be scattered throughout the galaxy, in forms we are only beginning to understand. As 3I Atlas arcs away from the Sun, its fate is sealed. It will escape the solar system, vanishing into the abyss from whence it came. Yet its legacy endures in the data it leaves behind. The chemical signatures etched into its coma, the clues hidden in its trajectory, and the whispers of its ancient age all serve as fragments of a larger cosmic narrative, one that connects the birth of stars, the evolution of planets, and the possibility of life beyond our corner of the galaxy. But what does this mean for humanity? The study of 3I Atlas is not merely an academic pursuit. It is a humbling reminder of our place in the universe. We are but temporary observers of a process that has played out countless times across the cosmos. Every atom in our bodies, every molecule in our oceans, and every grain of dust in our atmosphere may have once belonged to a comet like this one, or to a star that consumed it. And yet 3I Atlas offers hope. Its existence proves that the ingredients for complexity are not unique to our solar system. If comets can carry organic compounds, water, and even traces of heavy elements across galaxies, they may also serve as cosmic couriers, seeding nascent worlds with the raw materials for life. Perhaps in some distant system, a future civilization will one day discover a comet bearing the chemical fingerprints of our own. As we await the final chapters of 3I Atlas's journey, let us remember that this comet is not an anomaly. It is a bridge, Ampere's bridge between the familiar and the unknown, the past and the future, the finite and the infinite. In its icy heart lies a story waiting to be told, a story that transcends the boundaries of time and space. And as we listen, we are reminded that the universe is not a void, but a symphony, a chorus of comets, stars, and dreams, singing together across the endless dark. In the vast tapestry of the cosmos, where stars flicker like distant lanterns and galaxies swirl in endless spirals, the arrival of 3I Atlas marks a moment of profound significance. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, ATLAS, at Rio Hurtado, Chile, this interstellar comet enters our solar system as a visitor from the depths of the Milky Way. It is the third confirmed interstellar object to traverse our cosmic neighborhood, joining the enigmatic 1I Oumuamua and the more recent 2I Borisov. Yet, 3I Atlas carries with it a unique story, one etched in the icy veins of its nucleus and the gaseous whispers of its coma. Its journey began long before our solar system took shape, perhaps in the ancient thick disk of the galaxy, where time itself seems to stretch into eternity. Now, hurtling through the inner solar system at a blistering speed of 58 kilometers per second, it offers a fleeting glimpse into the secrets of interstellar space, a cosmic iceberg drifting through the void, bearing the fingerprints of a forgotten stellar nursery. As we peer into the heart of this traveler, we are reminded of our place in the universe, a fleeting speck in the grand expanse, yet privileged to witness the passage of a relic from another world. The discovery of 3I Atlas was not a mere accident, but a testament to the vigilance of modern astronomy. Initially catalogued as A11 Pel 3Z, the object's trajectory quickly raised eyebrows among observers. Its hyperbolic path, an unbound orbit that slants sharply through the solar system, spoke volumes of its interstellar origins. Unlike the elliptical orbits of native comets, which loop around the sun in predictable cycles, 3I Atlas's path is a straight, almost linear trajectory, a cosmic arrow fired from the galactic depths. The hyperbolic excess velocity of 58 kilometers per second, a speed far exceeding the gravitational grip of the sun, confirms that this comet is not a product of our stellar backyard. Instead, it is a transient wanderer, destined to depart once it has brushed past the sun's influence. This velocity is not merely a number. It is a narrative of motion, a story of acceleration and escape. As 3I Atlas plunges toward the Sun, the star's gravity imparts a temporary acceleration, propelling the comet to its peak speed of 68 kilometers per second at perihelion on 29 October 2025. Yet this acceleration is fleeting. Once the comet begins its retreat, the Sun's pull will decelerate it, though never enough to trap it in orbit. The comet's orbital eccentricity of 6.14 ns 0.02, the highest recorded among interstellar objects, underscores its defiance of gravitational capture. This parameter, a measure of the deviation from a perfect circle, paints a picture of a trajectory so elongated that it appears almost straight, a stark contrast to the graceful arcs of comets born within our solar system. The significance of 3I Atlas's hyperbolic path extends beyond its immediate dynamics. It serves as a cosmic Rosetta Stone, offering clues to the comet's origin. By tracing its trajectory backward, astronomers have determined that 3I Atlas entered the solar system from the direction of the constellation Sagittarius, near the galactic center. This origin point is not arbitrary. It situates the comet within the broader context of the Milky Way's structure. The galactic center, a region teeming with stars and shrouded in mystery, may hold the key to understanding how 3I Atlas was ejected from its native system. Perhaps it was flung outward by the gravitational chaos of a binary star system, or the violent expulsion from a protoplanetary disk. Whatever the mechanism, 3I Atlas now serves as a messenger, carrying with it the chemical and structural imprints of its birthplace. Yet the comet's journey is not merely one of physics and mathematics. It is a journey through time. If 3I Atlas hails from the thick disk of the Milky Way, a population of ancient stars that predates the Sun by billions of years, then this comet may be older than our solar system itself. Estimates suggest it could be between 7.6 and 14 billion years old, a staggering age that places it in the twilight of galactic history. To contemplate this is to grapple with the enormity of cosmic time. While human civilization spans mere millennia, 3I Atlas has traversed the galaxy for eons, its nucleus a frozen archive of primordial material. In this sense, the comet is not just a visitor, it is a time capsule, a relic of an era when the Milky Way was young and the universe was in its infancy. Beneath the shimmering veil of its coma lies the nucleus of 3I Atlas, a solid core of ice and rock that holds the secrets of its interstellar voyage. Though the nucleus remains obscured by the gaseous haze of the coma, observations by the Hubble Space Telescope suggest its diameter ranges between 0.32 and 5.6 kilometers, with the most probable size being less than 1 kilometer. This diminutive size belies the comet's immense significance. Despite its modest dimensions, 3I Atlas is a powerhouse of volatile activity. As it approaches the Sun, solar radiation penetrates its outer layers, heating the icy nucleus and triggering the sublimation of frozen gases. This process transforms solid CO2, water ice, and other volatiles into gaseous form, releasing a cascade of particles that coalesce into the coma. The resulting spectacle is a dance of light and shadow, a luminous halo that expands as the comet draws closer to the Sun. The coma of 3I Atlas is not merely a passive envelope of gas and dust. It is a dynamic, evolving entity. High-resolution images from the Gran Telescopio Canarias reveal a coma with an elliptical shape, spanning up to 26,400 by 24,700 kilometers in diameter, a region larger than Earth itself. Yet this vastness is deceptive. From Earth, the coma appears as a mere 2 arcseconds in angular diameter, a testament to the comet's vast distance. Within this diffuse cloud, the interplay of light and matter tells a story of transformation. Small dust grains, ejected at velocities of 22 meters per second, are carried away by solar radiation pressure, forming a faint anti-solar tail that stretches tens of thousands of kilometers into space. Meanwhile, larger particles, moving at slower speeds, linger closer to the nucleus, creating a denser, more compact region. This stratification of dust grains is a fingerprint of the comet's activity, a record of its response to the Sun's relentless energy. What sets 3I Atlas apart from its solar system counterparts is the composition of its coma. Spectroscopic analysis conducted by the James Webb Space Telescope, JWST, and SPHEREX have unveiled a chemical profile that is both familiar and alien. The comet is unusually rich in carbon dioxide, with a CO2 to water ratio 8 times higher than typical comets. This abundance of CO2 suggests that 3I Atlas formed in a region where temperatures were cold enough for CO2 to condense into solid form, likely beyond the CO2 frost line of its parent star's protoplanetary disk. Such an origin implies that the comet's birthplace was a frigid, distant realm, where volatile ices could survive for eons without sublimation. Yet, the presence of water ice, water vapor, and carbon monoxide adds complexity to this narrative. These molecules, while common in comets, are typically found in lower concentrations in CO2-rich environments. Their CO existence in 3I Atlas's coma raises intriguing questions about the conditions under which the comet formed and evolved. Beyond CO2 and water, the coma of 3I Atlas harbors a menagerie of exotic compounds. The detection of cyanide gas, CN, and atomic nickel, Ni, by the Very Large Telescope VLT, has added to the comet's mystique. Cyanide, a molecule with a reputation for toxicity, is a common constituent of cometary comas, produced when carbon-based ices sublimate and fragment under solar radiation. However, the presence of atomic nickel, a metallic vapor, is less typical. While nickel emissions have been observed in other comets including the Interstellar 2I Borisov, the absence of corresponding iron vapor in 3I Atlas is puzzling. This discrepancy may hint at unique chemical processes at play in the comet's coma, perhaps involving the thermal decomposition of nickel-containing organic compounds. Theories proposed by researchers such as Rohan Rahatgaonkar suggest that nickel tetracarbonyl, a volatile nickel compound, could be a source of the observed vapor. If true, this would imply that 3I Atlas's coma is a laboratory of chemical reactions where sunlight and interstellar radiation drive transformations that mirror those occurring in distant stellar nurseries. Even more intriguing is the detection of carbonyl sulfide, OCS, a molecule rarely seen in cometary comas. OCS is a complex compound composed of carbon, oxygen, and sulfur, and its presence in 3I Atlas's coma suggests a rich chemical environment. The formation of OCS likely requires specific conditions, such as the interaction of carbon monoxide with hydrogen sulfide, a process that could occur in the comet's icy mantle, or within the coma itself. The scarcity of OCS in solar system comets makes its detection in 3I Atlas all the more significant, as it may provide insights into the chemical diversity of interstellar materials. Together, these molecular signatures paint a portrait of a comet that is both familiar and enigmatic, a cosmic iceberg that carries the echoes of its distant past into the present. As 3I Atlas draws closer to the Sun, its coma undergoes a transformation that deepens the mystery of this interstellar traveler. One of the most striking features observed in July and August 2025 is the sun-facing plume, a jet of dust and gas that extends toward the star rather than trailing away from it. This phenomenon, initially mistaken for a traditional cometary tail, is in fact a dynamic outflow of material ejected from the comet's sunlit hemisphere. The plume's orientation defies intuition, as it points directly toward the sun, a direction where one might expect the solar wind and radiation pressure to sweep particles away. Yet here is a stream of dust and gas flowing against the cosmic tide, a testament to the complex interplay of forces at work in the comet's vicinity. The formation of the sun-facing plume is intimately tied to the sublimation of ices on the comet's nucleus. As solar radiation penetrates the surface, it preferentially heats the sunlit side of the nucleus, causing volatile ices to transition directly from solid to gas. This rapid sublimation creates localized pockets of high-pressure gas, which erupt from the surface in bursts of activity. These eruptions carry with them dust particles, lofting them into the coma and forming the plume. The plume's elongated shape, stretching westward in the sky, is a direct consequence of the comet's motion relative to the Sun. As 3I Atlas hurtles along its hyperbolic trajectory, the ejected material is carried along with the comet's forward momentum, creating a jet that aligns with the direction of travel, rather than trailing behind it. This behavior is not entirely unprecedented in cometary science. Similar sun-facing jets have been observed in distant comets such as CTHA 2014, UN 271, Bernardinelli-Bernstein, suggesting that this phenomenon may be more common than previously thought. However, the prominence of the Plume in 3I Atlas is remarkable, particularly given the comet's interstellar origin. The fact that an object from another star system exhibits such a feature challenges assumptions about the universality of cometary processes. Is the formation of sun-facing plumes a fundamental characteristic of comets, regardless of their origin? Or does 3I Atlas possess unique properties that make it particularly prone to this kind of activity? These questions underscore the value of studying interstellar comets as analogues for understanding the broader population of comets in the galaxy. The sun-facing plume also has implications for the comet's overall activity and evolution. As material is ejected from the nucleus, the comet loses mass, a process that can significantly alter its trajectory over time. While the mass loss from 3I Atlas is relatively modest, estimated at 6 kilograms of small dust particles and 60 kilograms of large dust particles per second, it nonetheless contributes to the gradual reshaping of the nucleus. Over the course of its journey through the inner solar system, 3I Atlas may experience periodic outbursts, sudden increases in activity that could further enhance the plume's visibility. These outbursts, driven by the uneven distribution of volatile ices on the nucleus, may also lead to the formation of secondary jets or even the fragmentation of the nucleus itself. The latter possibility is particularly intriguing, as it would mark the first time an interstellar comet has been observed to disintegrate. Despite the wealth of observational data, the sun-facing plume remains an enigma. Its existence challenges conventional models of cometary activity, which often assume that outgassing is distributed evenly across the nucleus. The localized nature of the plume suggests that the nucleus of 3I Atlas is not a uniform body, but a patchwork of regions with varying compositions and thermal histories. Some areas may be rich in CO2 ice, while others contain water ice or other volatiles, leading to differential sublimation rates. Additionally, the presence of a crust or insulating layer on the nucleus could influence the rate at which heat is transferred to the interior, further complicating the picture. These factors highlight the complexity of cometary evolution and the need for continued observation as 3I Atlas continues its journey. As the sun-facing plume fades into the cosmic backdrop, it leaves behind a lingering question. What other surprises await us as we study this interstellar visitor? The plume is not merely a curiosity. It is a window into the processes that govern the behavior of comets across the galaxy. By unraveling the mechanisms behind its formation, we gain insights into the broader tapestry of planetary science, where the icy remnants of stellar nurseries shape the evolution of entire systems. In the case of 3I Atlas, the sun-facing plume is a reminder that even in the vast solitude of interstellar space, the dance of light and shadow continues, an eternal ballet choreographed by the forces of the universe. Amid the scientific discourse surrounding 3I Atlas, a provocative hypothesis emerged, challenging the prevailing consensus. On 16 July 2025, astrophysicist Avi Loeb and colleagues from the Initiative for Interstellar Studies published a paper on Arxiv positing that 3I Atlas could be an extraterrestrial spacecraft. This assertion was based on several perceived anomalies: the comet's seemingly large size, the absence of detectable chemical signatures, and its trajectory's alignment with the solar system's ecliptic plane. Loeb and his team argued that these features, while explicable through natural processes, warranted further consideration as potential indicators of artificial origins. The hypothesis, while speculative, ignited a firestorm of debate within the astronomical community. Critics swiftly countered that the evidence supporting the extraterrestrial spacecraft theory was insufficient. Chris Lintert, a prominent figure in public science engagement, dismissed the idea as unfounded, noting that the vast majority of observational data pointed unequivocally to 3I Atlas's natural origin. Live Science echoed this sentiment, reporting that the scientific community overwhelmingly regarded the comet as a typical interstellar object. Researchers such as Darrell Seligman, who led one of the first studies on 3I Atlas, emphasized the wealth of evidence confirming its cometary nature. Spectroscopic analysis by the James Webb Space Telescope JWST, and the Swift Observatory had already detected CO2, water, carbon monoxide, and cyanide in the comet's coma, compounds commonly associated with cometary activity. Furthermore, the detection of atomic nickel vapor by the Very Large Telescope, VLT, aligned with observations of other comets, reinforcing the conclusion that 3I Atlas was a natural, if unusual, object. The controversy surrounding Loeb's hypothesis extended beyond the scientific merits of the argument. Many researchers expressed disappointment that the paper had garnered attention in a field where rigorous, data-driven inquiry is paramount. Samantha Lawler, an astronomer specializing in interstellar objects, highlighted the importance of distinguishing between testable hypotheses and speculative conjecture. She argued that while open-mindedness is essential in scientific exploration, extraordinary claims require extraordinary evidence, a standard that Loeb's theory had not met. The debate also raised questions about the role of media in shaping public perception of scientific discoveries. The rapid dissemination of Loeb's hypothesis through news outlets, despite its lack of empirical support, underscored the challenges of communicating nuanced scientific findings in an era of instant information. Despite the skepticism, the discussion prompted a broader conversation about the nature of interstellar objects and the limitations of current observational techniques. Loeb himself acknowledged that the most likely outcome was that 3I Atlas was a natural comet, but he defended his hypothesis as a thought experiment rather than a definitive claim. He argued that exploring unconventional ideas, even those with low probability, was a necessary part of scientific progress. This perspective resonated with some researchers who saw value in fostering creative thinking, provided it was grounded in rigorous methodology. Ultimately, the controversy surrounding 3I Atlas served as a reminder of the delicate balance between curiosity and caution in the pursuit of knowledge. While the comet's true nature remained firmly rooted in the realm of natural phenomena, the debate it inspired reflected the enduring human quest to understand the cosmos, and perhaps one day to recognize the signs of intelligence beyond our own. As 3I Atlas hurtles toward its closest approach to the Sun on 29 October 2025, its legacy as a transient visitor to the solar system is already being etched into the annals of astronomical history. The comet's journey, though brief, has offered a unique opportunity to study an object that carries the imprint of a distant stellar system. Its hyperbolic trajectory, rich chemical composition, and dynamic activity have provided invaluable insights into the processes that shape comets across the galaxy. Yet, the most profound lesson of 3I Atlas may lie in its role as a bridge between the familiar and the unknown. By observing this interstellar traveler, we are not only deciphering the history of a single comet, but also glimpsing the broader story of planetary formation in the Milky Way. The study of 3I Atlas has already challenged existing models of comet formation and evolution. Its unusually high CO2 abundance, for instance, suggests that the comet may have originated in a protoplanetary disk with distinct chemical conditions, compared to those in our own solar system. This finding could necessitate a re-evaluation of how comets are formed in different stellar environments and the role of interstellar radiation in shaping their compositions. Similarly, the detection of atomic nickel and carbonyl sulfide in the coma highlights the chemical diversity of interstellar materials, expanding our understanding of the molecular building blocks available in the cosmos. These discoveries, though rooted in the specifics of 3I Atlas, have implications that extend far beyond its individual journey. They contribute to a growing body of evidence that the ingredients for life, water, complex organic molecules, and metals are not unique to our corner of the galaxy but are widespread throughout interstellar space. The controversy surrounding the extraterrestrial spacecraft hypothesis, while ultimately resolved in favor of a natural origin, has also had a lasting impact. It has underscored the importance of maintaining a rigorous, evidence-based approach to scientific inquiry, even in the face of tantalizing possibilities. At the same time, it has reminded us that the universe is vast and filled with mysteries that defy easy explanation. The willingness to entertain unconventional ideas, while tempered by skepticism, is a hallmark of scientific progress. In this sense, 3I Atlas serves as a testament to the human spirit of exploration, the drive to question, to imagine, and to seek answers in the infinite expanse of space. As the comet continues its journey beyond the solar system, it carries with it the hopes and aspirations of those who have studied it. Its departure will not mark the end of its significance, but rather the beginning of a new chapter in our understanding of the cosmos. Future generations of astronomers will look back on 3I Atlas as a pivotal moment in the exploration of interstellar objects, a milestone that opened new avenues for research and inspired new questions. And perhaps one day, when a future interstellar visitor arrives, we will be better prepared to decode its message, to recognize its origins, and to appreciate its role in the grand tapestry of the universe. Until then, 3I Atlas remains a fleeting yet enduring symbol of the wonders that await us among the stars. In the vast, silent expanse of the universe, where the light of distant stars flickers like ancient sentinels, a solitary traveler emerged from the depths of interstellar space. Discovered on 1 July 2025 by the Atlas Survey telescope in the arid plains of Rio Hurtado, Chile, 3I Atlas, a comet born in another star system, has ignited a quiet revolution in human understanding of the cosmos. This icy wanderer, hurtling through the solar system at a blistering 58 kilometers per second, is neither a relic of our own celestial neighborhood nor a fleeting shadow of a passing asteroid. It is a messenger from the Milky Way's distant reaches, a fragment of a forgotten world that has traversed the void for eons to brush against the sun's warmth. As we peer into the heart of 3I Atlas, we are not merely observing a comet. We are bearing witness to a cosmic nomad, a testament to the dynamic, interconnected nature of our galaxy. Its arrival stirs questions that echo across millennia. What secrets does it carry from its birthplace? How do stars forge such travelers? And what tales do they tell of alien worlds? In its frozen nucleus, in the swirling coma of gas and dust, lies a story that transcends the boundaries of time and space. And as humanity turns its gaze skyward, we find ourselves humbled by the realization that we are not alone in the universe. We are part of a grander tapestry, woven together by the threads of starlight and stardust. To understand 3I Atlas is to unravel the intricate dance of physics and chemistry that governs the life of a comet. At its core lies a nucleus, a chaotic, icy hark composed of frozen volatiles, such as carbon dioxide, water, and methane, interspersed with silicates and organic compounds. This nucleus, cloaked in a veil of dust and gas, is the source of the comet's activity. As 3I Atlas ventures closer to the sun, solar radiation penetrates its fragile surface, sublimating the ices into vapor. This process, akin to a slow-burning fire, releases torrents of gas and particulate matter, forming the luminous coma that surrounds the nucleus and the iconic tail that stretches millions of kilometers into space. What sets 3I Atlas apart from its solar system counterparts is its hyperbolic trajectory, a path that defies the gravitational embrace of the sun. Unlike the elliptical orbits of native comets, which return periodically to the inner solar system, 3I Atlas's orbit is open-ended. Its velocity, exceeding the escape velocity of the solar system, ensures that it will never return. This trajectory, confirmed by precise measurements of its orbital eccentricity, 6.14141, is a fingerprint of its interstellar origin. The comet's arrival is not the result of a gentle gravitational nudge from a passing planet or star, but a collisionless journey through the cold, dark corridors of interstellar space. The composition of 3I Atlas further deepens its enigma. Observations by the James Webb Space Telescope reveal a coma rich in carbon dioxide, with traces of water ice, carbon monoxide, and carbonyl sulfide. These molecules, preserved in a primordial state, offer clues about the conditions of the protoplanetary disk where 3I Atlas was born. The detection of cyanide gas and atomic nickel vapor adds another layer of complexity, suggesting a history of violent collisions or exposure to extreme stellar environments. Yet, for all its strangeness, 3I Atlas shares familiar traits with comets in our own system. Its reddish hue, its dusty coma, and its ability to outgas material as it dances with the sun. The nucleus itself remains shrouded in mystery. Estimates suggest it measures less than 1 kilometer in diameter, a mere speck compared to the colossal worlds of the outer solar system. Yet this small body holds immense significance. Its size implies a delicate balance between the forces of solar heating and structural integrity. Too close to the sun, and it risks disintegration. Too far, and it remains dormant, a silent wanderer. The fact that 3I Atlas has survived its journey across interstellar space speaks to the resilience of such objects and the harsh yet fascinating environments they endure. The study of 3I Atlas is not merely an academic pursuit. It is a voyage into the unknown, a quest to decipher the handwriting of the universe. Every observation, every spectrum of light captured by Earth-based and spaceborne telescopes adds another piece to the puzzle of its origin and evolution. The Hubble Space Telescope's high-resolution images have revealed the comet's coma in exquisite detail, tracing the distribution of dust and gas as it evolves under the sun's influence. The James Webb Space Telescope's infrared capabilities have peered through the veil of dust to analyze the molecular composition of the coma, uncovering the presence of carbon dioxide isotopes and hinting at the comet's ancient lineage. These findings challenge our assumptions about the uniformity of cometary composition across the galaxy. While 3I Atlas shares similarities with solar system comets, its unusually high carbon dioxide content suggests a formation environment distinct from our own. Did it originate in the frigid outer reaches of its parent star's protoplanetary disk, where CO2 frost lines allow the molecule to condense? Or was it forged in a turbulent, radiation-rich zone near a dying star? The answers lie buried in the comet's chemistry, waiting to be unearthed by the instruments of human ingenuity. Beyond its physical properties, 3I Atlas invites philosophical reflection. Its age, estimated at 7 to 14 billion years, predates the solar system itself. It is a relic of a bygone era, a survivor of epochs when stars were young and galaxies were in their infancy. To gaze upon 3I Atlas is to look back in time, to touch the echoes of a cosmic history that predates Earth's existence. In its journey, we see the impermanence of celestial structures, the rise and fall of stars, the birth and death of planetary systems, and the ceaseless recycling of matter across the galaxy. Yet, 3I Atlas is not a passive relic. It is an active participant in the cosmic drama, shaping and being shaped by the forces of the universe. As it approaches perihelion on 29 October 2025, its activity will intensify. The sublimation of volatile ices will accelerate, spewing plumes of gas and dust into space. These eruptions, visible as jets and tails, are not random. They are the comet's response to the sun's energy, a final act of transformation before it departs the solar system forever. The study of 3I Atlas also highlights the limitations of our current understanding. Despite decades of research on comets, this object reveals gaps in our knowledge. For instance, the absence of certain carbon chain compounds in its coma defies expectations, while the timing of its activity raises questions about the mechanisms driving its outgassing. These mysteries remind us that the universe is vast, complex, and often unpredictable. Every answer we uncover begets new questions, propelling us forward in our search for truth. As 3I Atlas hurtles toward its closest approach to the sun, the stage is set for a spectacle of cosmic proportions. Yet, this is not the end of the story. The data collected now will ripple through the scientific community, inspiring new models of comet formation, interstellar dynamics, and the chemistry of the early universe. Future missions, equipped with advanced instrumentation, may one day intercept such interstellar visitors, returning samples to Earth for direct analysis. Until then, we are left to ponder the significance of 3I Atlas, not just as an object of study, but as a symbol of humanity's enduring curiosity. In the coming weeks, as the comet's coma expands and its tail grows longer, we will bear witness to the raw power of the sun and the fragility of a traveler from the stars. But beyond the science lies a deeper truth. 3I Atlas reminds us that the universe is not a static, isolated realm. It is a living, breathing entity where matter and energy flow freely, connecting distant worlds in ways we are only beginning to comprehend. And as we track this interstellar wanderer across the heavens, we are reminded that we, too, are part of this cosmic web, a fleeting spark in an eternal flame. The universe is a vast tapestry of light and shadow, where galaxies spiral in endless dance, and stars are born and die in cycles as ancient as time itself. Yet within this grand symphony, there exist quieter messengers, interstellar travelers, that drift silently through the void, bearing secrets from distant corners of the cosmos. One such messenger arrived in 2025, a comet named 3I Atlas, whose journey through our solar system ignited a new chapter in humanity's quest to understand the origins of the universe. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas in Chile, 3I Atlas was not a fleeting visitor, but a relic of cosmic antiquity. Its trajectory, a hyperbolic arc defying the gravitational embrace of the Sun, marked it as the third confirmed interstellar object to pass through our neighborhood, following the enigmatic 1I Oumuamua and 2I Borisov. Yet, unlike its predecessors, 3I Atlas carried with it a unique signature, a coma rich in carbon dioxide, a composition that hinted at a birthplace far removed from the familiar architecture of our solar system. As telescopes turned their gaze toward this icy wanderer, astronomers found themselves staring into a mirror, reflecting the chaotic beauty of a universe teeming with mysteries. What makes 3I Atlas so extraordinary is not merely its interstellar origin, but the questions it raises about the cosmos. How did it form in the cold depths of interstellar space? What forces propelled it toward the Sun? And what story does its composition tell about the environments of distant stars? To unravel these threads, we must peer beyond the comet's glowing coma and into the heart of its journey, a journey that transcends the boundaries of time and space. At the heart of 3I Atlas's story lies a paradox. It is both a product of the universe's indifference and a testament to its creativity. The comet's hyperbolic trajectory, defined by an orbital eccentricity of 6.141, ensures that it will never return to the Sun. Unlike the elliptical paths of most comets, which loop around their host stars, 3I Atlas's path is a straight line drawn by the laws of physics, a line etched by its velocity of 58 kilometers per second, far exceeding the escape velocity required to flee the solar system. This speed, its hyperbolic excess velocity Vn, is a relic of its origin, a velocity imparted by gravitational interactions in its home system, or the chaotic dance of stars in the Milky Way. The discovery of 3I Atlas was not a moment of serendipity, but a triumph of modern astronomy. The Atlas telescope, designed to detect near-Earth objects, captured the comet as it glided through the dense star fields near the galactic center. Initially mistaken for a potential hazard, its trajectory was soon revealed to be a cosmic detour. Follow-up observations by the Zwicky Transient Facility and the James Webb Space Telescope painted a picture of a comet actively outgassing, its nucleus cloaked in a coma of gas and dust. The Hubble Space Telescope's images, with their razor-sharp clarity, narrowed the comet's nucleus to a diameter of less than 1 kilometer, a stark contrast to the sprawling coma that stretched tens of thousands of kilometers. What drives this activity? The Sun, the great architect of cometary drama. As 3I Atlas approached the inner solar system, solar radiation began to sublimate its volatile ices, releasing clouds of carbon dioxide, water vapor, and carbon monoxide. This process, akin to a slow-motion volcanic eruption, created a coma that glowed with the faint red hue of organic compounds. The comet's early activity, detected by the Transiting Exoplanet Survey satellite TESS, as far back as May 2025, suggested a composition rich in ices that could sublimate at extreme distances from the Sun. Such behavior is rare among comets, which typically become active only when they cross the orbit of Jupiter. For 3I Atlas, its journey seemed to begin long before its discovery, a silent performance choreographed by the invisible hand of cosmic forces. Yet the comet's most intriguing feature is its chemical fingerprint. Observations by the James Webb Space Telescope revealed an unprecedented abundance of carbon dioxide in its coma, dwarfing the ratio seen in solar system comets. This anomaly hints at a formation environment far colder than the Kuiper belt, where ices like methane and ammonia dominate. Instead, 3I Atlas may have coalesced in a protoplanetary disk, where carbon dioxide froze into solid form, a condition achievable only at distances where the temperature drops below -200 degrees Celsius. The presence of water, ice, and vapor, though modest, suggests a secondary layer of complexity, one that challenges existing models of comet formation. Even as 3I Atlas hurtled toward perihelion, its story deepened. The detection of cyanide and atomic nickel in its coma by the Very Large Telescope added another layer of intrigue. These elements, typically associated with the violent chemistry of dying stars, raised questions about the comet's history. Had it wandered through nebulae, where stellar winds sculpted its surface? Or was it a survivor of a planetary system disrupted by a nearby supernova? Each observation peeled back another veil, revealing a puzzle that demanded answers not just from telescopes, but from the imagination of humankind. To trace 3I Atlas's origins is to embark on a journey through time and space, a voyage that spans billions of years and traverses the galactic plane. The comet's trajectory, which brought it from the direction of the galactic center, points to an origin in either the Milky Way's thin or thick disk. The thin disk, a younger, metal-rich population of stars, contrasts with the thick disk's ancient, metal-poor inhabitants. By analyzing the comet's velocity components, its radial, transverse, and vertical motion, astronomers determined that 3I Atlas's path is tilted relative to the galactic plane, suggesting it is a member of the thick disk. This classification implies an age of at least 7 billion years, making the comet potentially older than the solar system itself. Such an age is staggering. Imagine a world where the sun had not yet ignited, where the first stars flickered into existence in the darkness. 3I Atlas, a remnant of that primordial era, carries with it the chemical imprints of a cosmos still learning how to create complexity. Its composition, enriched in carbon dioxide and depleted in carbon chains, offers clues about the conditions of its birthplace. Was it forged in a protoplanetary disk around a dying star, where radiation fractured molecular bonds? Or did it form in the aftermath of a supernova, where shockwaves compressed gas and dust into icy nuclei? The answers lie buried in the comet's nucleus, a frozen archive of the universe's earliest chapters. Yet the comet's journey is not solely a tale of the past. Its passage through the solar system has sparked debates about the prevalence of interstellar objects and their role in shaping planetary systems. The fact that 3I Atlas originated from the southern celestial hemisphere, a region where telescopes have historically struggled to detect faint objects, challenges assumptions about the distribution of interstellar visitors. Are such comets more common than previously thought? Could they play a role in seeding life with organic molecules? Or do they serve as cosmic debris from failed planetary systems? These questions, unanswered, underscore the humility of human knowledge in the face of the infinite. The comet's trajectory also invites speculation about its future. After passing within 0.19 AU of Mars and 0.36 AU of Jupiter, it will vanish into the interstellar void, its hyperbolic path carrying it beyond the reach of even the most powerful telescopes. Yet, its legacy will endure. The data gathered from its brief visit, its spectral fingerprints, its dust emission rates, its rotational quirks, will fuel decades of research, perhaps even inspiring missions to intercept future interstellar visitors. For now, 3I Atlas remains a solitary figure, a ghostly reminder of the universe's vastness and the fragility of our place within it. As 3I Atlas recedes from view, it leaves behind a trail of questions that stretch far beyond its own journey. What other interstellar travelers await discovery, their stories waiting to be told? How will advancements in technology, from the Vera C. Rubin Observatory to next-generation spectrographs, reshape our understanding of these cosmic wanderers? And what might they reveal about the universality of planetary formation, the spread of life's building blocks, or the hidden architectures of the Milky Way? The comet's trajectory, its chemical composition, and its ancient age are not isolated phenomena, but threads in a larger narrative, the story of a universe in perpetual motion. Every atom in its nucleus, every molecule in its coma, whispers of epochs long past and possibilities yet to unfold. In tracing 3I Atlas's path, we do not merely observe a comet, we glimpse the interconnectedness of all things, the delicate balance between chaos and order that defines existence. And so, as the comet fades into the dark, its message lingers. The universe is not a static expanse, but a living, breathing entity, where every star, every planet, and every interstellar visitor plays a role in the unfolding saga of cosmic time. The next chapter, however, awaits not in the past, but in the future, a future where humanity's eyes turn once more to the stars, ready to listen. In the vast, silent expanse of the universe, where galaxies spiral like celestial dancers and stars are born in the crucibles of nebulae, a traveler stirs. 3I Atlas, an interstellar comet, hurtles through the solar system on a path etched by forces beyond our comprehension. Discovered in July 2025 by the Atlas Survey Telescope in Chile, this enigmatic visitor carries the secrets of distant stars and ancient epochs. Its arrival, a fleeting moment in cosmic terms, invites us to ponder the interconnectedness of all things, the delicate dance of matter and energy that binds the cosmos. 3I Atlas is not merely a rock or ball of ice. It is a messenger from the depths of the Milky Way, bearing fragments of a story older than our own solar system. Classified as the third confirmed interstellar object, after 1I Oumuamua and 2I Borisov, it arrives with a hyperbolic trajectory, a path too swift to be captured by the sun's gravity. Yet, as it glides past planets and planetary boundaries, it offers a glimpse into the raw material of other star systems, the building blocks of worlds yet unseen. This comet's journey is a testament to the dynamic, chaotic beauty of the universe. It does not belong here, yet it is here. It reminds us that the cosmos is not a collection of isolated islands, but a tapestry woven by time, motion, and chance. As scientists track its progress and unravel its mysteries, 3I Atlas becomes a symbol of humanity's enduring quest to understand the infinite. At the heart of 3I Atlas lies a paradox. Its very existence defies the familiar laws that govern the solar system. The comet's hyperbolic trajectory, with an eccentricity of 6.141, is a mathematical signature of its interstellar origin, unlike the elliptical orbits of planets and asteroids, which loop endlessly around the Sun. 3I Atlas's path is a straight line almost. This extreme eccentricity, combined with its hyperbolic excess velocity of 58 kilometers per second, 36 mmi, confirms that the comet is not bound to our star. It arrived from the Milky Way's depths, moving too swiftly to be ensnared by the sun's gravitational embrace. The discovery of 3I Atlas was a triumph of modern astronomy. Initially mistaken for a near-Earth object due to its rapid approach, it was soon revealed to be something far more extraordinary. Observations from the Hubble Space Telescope and the James Webb Space Telescope painted a picture of a comet unlike any seen before. Its nucleus, cloaked in a coma of gas and dust, emits carbon dioxide in quantities surpassing those of solar system comets. The presence of water ice, carbon monoxide, and even traces of cyanide and nickel adds to the intrigue. These molecules, forged in the cold crucible of interstellar space, whisper of the conditions in the comet's birthplace. The physics of 3I Atlas's activity is a ballet of sublimation and outgassing. As sunlight warms its surface, volatile ices transform directly into gas, carrying with them dust particles that form the comet's glowing coma. The sun's rays, though distant at 1.36 AU at perihelion, are sufficient to ignite this process. The comet's reddish hue, reminiscent of D-type asteroids, and the interstellar comet Borisov, hints at complex organic chemistry. These are the same processes that shaped the early solar system, yet here they unfold under the influence of a star far removed from our own. The significance of 3I Atlas's trajectory extends beyond its speed. Its path is aligned with the Ecliptic, the plane shared by the planets. Despite its retrograde motion, This alignment, statistically rare for interstellar objects, has sparked debates among scientists. Is it a random fluke, or does it hint at a deeper cosmic order? The answer may lie in the comet's origin, traced back to the direction of the galactic center. 3I Atlas may have formed in a stellar nursery, where gravitational interactions hurled it into the void. Or perhaps it is a relic of the Milky Way's ancient history, older than the solar system itself. The study of 3I Atlas is a voyage into the unknown, a search for answers to questions that transcend the comet itself. Where did it come from? What star system birthed it? And why does it carry so much carbon dioxide? A molecule that in our own solar system is associated with the outermost reaches of the Kuiper belt. These questions are not merely academic. They are keys to understanding the universality of planetary formation. Astronomers have estimated the comet's age by analyzing its trajectory and velocity. If it hails from the Milky Way's thick disk, a population of stars older than our own, then 3I Atlas could be between 7.6 and 14 billion years old. That would make it a relic from the galaxy's youth, a time when stars were forming at an accelerated pace. Such an age challenges our perception of the cosmos. If a comet can survive for billions of years in interstellar space, what else might endure? What other ancient travelers might one day cross our path? The comet's composition provides further clues. The high abundance of carbon dioxide in its coma suggests that 3I Atlas formed far from its parent star, beyond the CO2 frost line, where temperatures allow the molecule to freeze. This parallels the formation of comets in the solar system, but implies that its parent star system had a different architecture. Perhaps the star was smaller, or the protoplanetary disk extended farther. Alternatively, the comet may have formed in a binary star system, where gravitational perturbations could scatter objects to great distances. Yet for all the data, 3I Atlas remains an enigma. Its nucleus, shrouded in a veil of dust, is difficult to measure precisely. Estimates place its diameter between 0.32 and 5.6 kilometers, but the true value may be at the lower end. The comet's rotation period, determined through painstaking analysis of brightness variations, is approximately 16 hours, a rhythm that echoes the slow spin of other comets. But as 3I Atlas approaches the Sun, its activity may alter this cadence. Will the outgassing of volatiles create a wobble? Will its shape change as it sheds mass? These uncertainties underscore the fragility of cosmic bodies and the dynamic nature of their evolution. The debate over 3I Atlas's origins is not limited to its physical properties. Its trajectory, nearly aligned with the ecliptic, has sparked speculation about its journey through the galaxy. Could it have passed near other stars, its path nudged by their gravity? Simulations suggest that in the past 10 million years, 3I Atlas may have ventured within 1 parsec, 3.3 light-years, of 25 known stars. Each encounter would have left a mark, a subtle shift in its velocity or direction. These gravitational tugs of war are the unseen forces that shape the destinies of interstellar objects, scattering them across the galaxy like seeds carried by the wind. As 3I Atlas continues its journey, it invites us to confront the limits of human knowledge. Every observation brings clarity to some questions while deepening others. The detection of atomic nickel and cyanide in its coma, for instance, aligns with the chemistry of solar system comets, but defies easy explanation. Why does it emit these elements? Is it a product of unique conditions in its parent star system, or do such emissions occur more frequently than we realize? The answers lie in the data, yet the data are incomplete. This uncertainty has fueled both scientific rigor and imaginative speculation. Among the most controversial claims is the suggestion by astrophysicist Avi Loeb that 3I Atlas might be an artificial object, an extraterrestrial spacecraft. Loeb's hypothesis rests on the comet's unusual trajectory and apparent lack of identifiable chemicals, but these assertions have been met with skepticism. Countless telescopic observations have confirmed the comet's cometary activity, outgassing of CO2, water vapor, and cyanide. The absence of certain compounds may simply reflect the distance from the Sun or the comet's evolutionary history. The debate underscores a fundamental tension in science: the need to remain open to the unexpected while adhering to the standards of evidence. Loeb's hypothesis, though provocative, lacks the empirical foundation to elevate it beyond speculation. As astronomer Darrell Seligman notes, there have been numerous telescopic observations of 3I Atlas demonstrating that it's displaying classical signatures of cometary activity. The scientific community, while always open to new ideas, demands extraordinary evidence for extraordinary claims. Yet, even in the face of skepticism, the idea of an alien artifact lingering in the cosmos is undeniably compelling. It speaks to our deepest hopes and fears that we are not alone, that the universe may harbor minds capable of shaping matter as we do. But 3I Atlas, for now, remains a comet, AMPA's natural object born of starlight and shadow, drifting through the void on a path dictated by gravity and chance. As the comet recedes from the solar system, its story is far from over. Future generations of telescopes, perhaps even a spacecraft launched from Mars, may one day revisit its trail. Until then, 3I Atlas stands as a reminder of the universe's capacity to surprise and inspire. It is a wanderer, a witness to the birth and death of stars, and a bridge between the known and the unknown. In its fleeting passage, we see not only the grandeur of the cosmos, but the humility of our place within it. The journey of 3I Atlas is a microcosm of humanity's scientific endeavor, a blend of curiosity, perseverance, and the occasional leap of imagination. As this interstellar comet continues its solitary trek through the galaxy, it leaves behind a legacy of questions and discoveries. It challenges our assumptions about the origins of comets, the dynamics of the Milky Way, and the possibility of life beyond Earth. Yet, for all its mysteries, 3I Atlas is ultimately a natural phenomenon, a product of the same cosmic forces that gave rise to the solar system and the stars. Its story is not just about a single object, but about the collective effort of scientists, engineers, and dreamers who strive to understand the universe. From the Atlas telescope that first spotted its faint glow, to the James Webb Space Telescope that dissected its chemical makeup, every tool and technique represents a step forward in our quest for knowledge. 3I Atlas reminds us that the cosmos is a place of wonder, where even the smallest speck of light can hold the key to profound truths. As we watch 3I Atlas fade from view, we are left with a sense of awe and anticipation. The universe is vast, and its stories are countless. In the silence between the stars, there are whispers of other travelers waiting to be discovered, each one a thread in the intricate tapestry of existence. And perhaps in some distant corner of the galaxy, another civilization gazes at the heavens, wondering if one day, a comet from their world might find its way to ours. Until then, 3I Atlas remains a beacon of cosmic curiosity, a reminder that the universe is not a static backdrop, but a living, breathing entity. Its passage through the solar system is a fleeting moment in the grand scale of time, yet it is enough to ignite the imagination and propel us ever onward in our search for meaning among the stars. In the vast tapestry of the cosmos, where galaxies swirl in silent dance and stars burn with the fire of creation, a solitary traveler glides through the vacuum of interstellar space. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas at Rio Hurtado, Chile, 3 Atlas stands as the third interstellar object ever confirmed to have ventured into our solar system. Its arrival is a quiet yet profound event, a fleeting whisper from the depths of the Milky Way, carrying secrets of distant stellar nurseries and the turbulent history of its birthplace. Unlike the familiar comets born in our own cosmic backyard, 3 Atlas hails from a realm beyond the sun's gravitational embrace. It is a wanderer, a relic of a forgotten epoch, and a testament to the dynamic interconnectedness of the universe. As it hurtles through the inner solar system at a blistering speed of 58 kilometers per second, 3I Atlas defies the gentle curves of planetary orbits. Its path is a hyperbolic arc, a trajectory so extreme that it will escape the sun's pull entirely, continuing its journey into the uncharted void. This comet is not merely a visitor, it is a messenger, bearing the chemical fingerprints of a foreign star system. From its icy nucleus to the glowing coma of gas and dust, Every detail of 3i Atlas offers a window into the conditions of its origin, what stirs within its frozen heart, what forces shaped its journey across the galactic expanse, and what does its passage reveal about the nature of our place in the universe. The story of 3i Atlas is one of discovery and wonder, of humanity's relentless pursuit to understand the cosmos. It is a reminder that the universe is teeming with mysteries waiting to be unraveled, and that even the smallest, faintest object can ignite the imagination of scientists and dreamers alike. As we peer through the eyes of our telescopes and trace the comet's path across the heavens, we are reminded of our shared curiosity and the boundless possibilities that lie beyond the stars. The discovery of 3i Atlas was not a sudden revelation, but a gradual unfolding of clues pieced together by the collective effort of astronomers around the globe. On that fateful evening in July 2025, the Atlas Survey telescope captured an anomaly, a faint, moving object nestled within the dense star fields of the galactic center. At first glance, it appeared unremarkable, a mere smudge against the backdrop of countless stars. Yet, as the data was scrutinized, its true nature began to emerge. The object's velocity, 61 kilometers per second, relative to the Sun, was unprecedented. It was moving far too fast to be bound by the solar system's gravity, its path curving in a way that defied the gentle ellipses of ordinary comets and asteroids. The initial days following its discovery were a flurry of activity. Professional and amateur astronomers alike turned their telescopes toward the skies, eager to confirm the object's trajectory. Observations from the Zwicky Transient Facility, ZTF, and the Canada-France-Hawaii Telescope, CFHT, revealed a critical truth. 3i Atlas was on a hyperbolic path, its orbital eccentricity exceeding 6.141. Such a number meant it had originated from outside the solar system, its journey beginning in the distant reaches of the Milky Way. Yet the question remained, was it a comet or an asteroid? Early reports were inconclusive, with some observers noting no clear cometary features. But as the weeks progressed, the evidence mounted. By late July, telescopes such as the Deep Random Survey SAX-09 and the Lowell Discovery Telescope G37 captured faint but unmistakable signs of a coma, a halo of gas and dust encircling the nucleus, a hallmark of cometary activity. The confirmation of 3i Atlas's interstellar origin was a triumph of modern astronomy. It marked the third such object to be identified since the enigmatic 1i Oumuamua in 2017 and the more recent 2i Borisov in 2019. Yet 3i Atlas stood apart in ways both subtle and profound. Its trajectory, nearly aligned with the ecliptic plane, the orbital plane shared by the planets, was a cosmic coincidence that intrigued researchers. Unlike its predecessors, which hailed from the northern celestial hemisphere, 3i Atlas emerged from the south, a direction long thought to be underrepresented in interstellar visitors. This anomaly hinted at the possibility that our models of interstellar object distribution might be incomplete, urging scientists to reconsider the mechanisms that govern their paths. The early observations also revealed a puzzle. Why had 3i Atlas not been spotted sooner? The answer lay in its surroundings. The galactic center, a region teeming with stars and nebulae, created a visual cacophony that masked the comet's presence. It was only when the object drifted into clearer skies that its true nature could be discerned. This serendipity underscored the challenges of detecting interstellar visitors, objects that are often faint, fast-moving, and embedded in the cosmic noise. Yet the perseverance of the astronomical community, armed with cutting-edge technology and a shared sense of purpose, ensured that 3i Atlas would not vanish into obscurity. As the weeks unfolded, the comet's story deepened. Follow-up observations by the Nordic Optical Telescope and the Tidy Observatory confirmed that 3i Atlas was clearly active, its coma growing brighter and more expansive. The red hue of its dust, similar to that of 2i Borisov, hinted at a composition shaped by ancient stellar processes. Each new piece of data added another thread to the tapestry of understanding, weaving together the threads of chemistry, dynamics, and cosmology. 3i Atlas was not just a passing curiosity. It was a cosmic enigma demanding to be unraveled. To comprehend the significance of 3i Atlas, one must first grasp the mechanics of its journey. Unlike the comets that originate in the Kuiper belt or the Oort cloud, 3I Atlas is not bound by the sun's gravity. Instead, it follows a hyperbolic trajectory, a path so elongated that it intersects the solar system only briefly before fleeing into the void. This trajectory is defined by its hyperbolic excess velocity of 58 kilometers per second, a speed that dwarfs the velocities of 1I Oumuamua, 26 kilometers per second, and 2I Borisov, 32 kilometers per second. Such a velocity suggests that 3I Atlas has traveled vast distances across the Milky Way, its path shaped by the gravitational tugs of distant stars and the unseen architecture of the galactic disk. The comet's closest approach to the Sun, its perihelion, will occur on 29 October 2025 at a distance of 1.36 astronomical units, AU. This places it between the orbits of Earth and Mars, a region where the Sun's heat will drive intense cometary activity. As the comet's icy nucleus warms, volatile ices will sublimate, releasing plumes of gas and dust that form its coma and tail. These phenomena, though familiar from solar system comets, take on new meaning in the context of an interstellar traveler. The composition of 3I Atlas's coma, as revealed by the James Webb Space Telescope, JWST, is particularly intriguing. Rich in carbon dioxide and containing traces of water ice, carbon monoxide, and carbonyl sulfide, it offers a glimpse into the chemical environment of its home system. The presence of cyanide and atomic nickel, detected by the Very Large Telescope, VLT, adds another layer of complexity, hinting at processes that may differ from those seen in native comets. The comet's origin story is equally captivating. By analyzing its trajectory, astronomers have traced its path back to the direction of the Milky Way's thick disk, a region populated by ancient stars with lower metallicity than the Sun. If this origin is confirmed, 3I Atlas could be over 7 billion years old, predating the solar system itself. Such an age raises profound questions. What cataclysmic event propelled it from its cradle into the interstellar abyss? Did it form in the shadow of a dying star? Or was it ejected by the gravitational chaos of a young planetary system? The answers remain elusive, but the possibility that 3I Atlas carries the remnants of an ancient world, perhaps one long since consumed by time, adds a haunting beauty to its journey. The comet's interaction with the solar system, though brief, is not without consequence. Its closest approach to Mars at 0.19 AU on 3 October 2025, and its near miss with Jupiter on 16 March 2026, offer opportunities to study its behavior under the influence of planetary gravity. These encounters, though insufficient to alter its trajectory significantly, provide valuable data on the comet's resilience. Will its nucleus fragment under the stress of tidal forces, or will it endure? A testament to the strength of its frozen core. The answers will shed light on the structural integrity of interstellar comets and the conditions necessary for their survival across interstellar distances. Yet the most compelling aspect of 3I Atlas's journey lies in its potential to reshape our understanding of the cosmos. As a visitor from another star system, it serves as a cosmic bridge, connecting the Sun's domain to the vast unexplored regions of the galaxy. Its passage reminds us that the universe is not a static expanse, but a dynamic web of motion and exchange. Every interstellar object, from 1I Oumuamua to 3I Atlas, is a thread in this web, weaving together the stories of stars, planets, and the forces that govern them. Observing 3I Atlas is no small feat. Despite its interstellar significance, the comet is a faint object, its peak brightness expected to be no higher than apparent magnitude 11.5, an object invisible to the naked eye and challenging even for amateur astronomers with modest equipment. Its dimness is compounded by its trajectory, which brings it perilously close to the Sun in October 2025, rendering it invisible from Earth during its perihelion passage. This solar conjunction necessitates innovative strategies, such as relying on Mars-orbiting spacecraft to capture images of the comet during its closest approach to the red planet. The challenges extend beyond visibility. The comet's coma, while rich in chemical diversity, is a veil that obscures the true nature of its nucleus, determining the size of 3I Atlas's nucleus. A crucial step in understanding its origins and evolution requires disentangling the light from the coma and the nucleus itself. High-resolution imaging by the Hubble Space Telescope has provided estimates ranging from 0.32 to 5.6 kilometers, but the uncertainty remains significant. This ambiguity underscores the limitations of current observational tools and the need for advanced technologies to pierce the veil of cosmic dust. Yet the obstacles faced by astronomers are matched by the ingenuity of their methods. The Vera C. Rubin Observatory, newly commissioned in 2025, has already captured images of 3I Atlas, offering insights into the growth of its coma over time. The Transiting Exoplanet Survey satellite, TESS, though designed to hunt for exoplanets, serendipitously tracked the comet's activity from May to June 2025, revealing that it was already bright and active at a distance of 6.4 AU from the Sun. These unexpected contributions highlight the interconnectedness of modern astronomical research, where instruments built for one purpose often yield discoveries in entirely different domains. Looking ahead, the coming months will see a crescendo of observations. As 3I Atlas reaches its peak activity, the Hubble Space Telescope will conduct ultraviolet spectroscopy to analyze the comet's gas emissions and sulfur-to-oxygen ratio, while the James Webb Space Telescope will continue monitoring its CO2-rich coma. These data will not only refine our understanding of 3I Atlas, but also contribute to the broader study of interstellar objects. What patterns emerge from their chemical compositions? Do these objects share common origins, or do they reflect the diverse histories of countless star systems? As the comet departs the solar system, its legacy will endure in the data it leaves behind. Each pixel of light captured, each spectral line recorded, is a piece of a puzzle that spans the vastness of space and time. 3I Atlas is more than an interstellar visitor. It is a beacon, guiding us toward a deeper comprehension of the universe's interconnected nature. And as we turn our gaze to the stars, we are reminded that the cosmos is not a silent expanse, but a symphony of motion, where every object, no matter how distant, has a story to tell. In the vast silent expanse of the cosmos, where the stars burn like ancient sentinels and the void stretches beyond imagination, a lone traveler glides through the solar system. 3I Atlas, a comet born of interstellar origins, drifts on a path that defies the gravitational embrace of our Sun. Discovered in July 2025 by the Asteroid Terrestrial Impact Last Alert System, ATLAS, in Chile, this icy wanderer is the third confirmed interstellar object to ever be observed within our cosmic neighborhood. Unlike the familiar comets that originate in the Kuiper Belt or Oort cloud, 3I Atlas hails from a realm far removed from our own, a place shrouded in the mysteries of distant stellar systems. Its arrival is a fleeting glimpse into the broader galactic tapestry, a reminder that we are not alone in the universe, but merely one thread in an immense cosmic loom. What sets 3I Atlas apart is not just its origin, but the enigmatic nature of its journey. Moving at a blistering speed of 58 kilometers per second relative to the Sun, it follows a hyperbolic trajectory that will carry it out of the solar system forever. This velocity, far exceeding the escape velocity of the Sun's gravitational pull, confirms its interstellar heritage. Yet, as it approaches perihelion, the point in its orbit closest to the Sun, it becomes a laboratory of cosmic chemistry, its icy nucleus releasing gases and dust that whisper secrets of its birthplace. To study 3I Atlas is to peer into the frozen remnants of another star's planetary system, a relic of a time when the Milky Way was young and its stars were cradling nascent worlds. The story of 3I Atlas is one of discovery, curiosity, and awe. From its first detection in the dense star fields near the galactic center to the revelations uncovered by the James Webb Space Telescope and ground-based observatories, every observation adds a brushstroke to a portrait of a universe teeming with lifeless, yet breathtaking beauty. As we trace its path through the inner solar system, we are reminded of our smallness and the infinite grandeur that surrounds us. The discovery of 3I Atlas began with a faint smudge of light in the night sky, a speck of dust and ice hurtling through the solar system at 61 kilometers per second, detected by the Atlas survey telescopes on 1 July 2025. Its trajectory quickly raised eyebrows among astronomers. Initial calculations revealed that the object was not bound to the sun's gravity. Instead, it was racing on a hyperbolic path, destined to escape the solar system entirely. This trajectory, defined by an orbital eccentricity of 6.141, is one of the most extreme ever recorded for an interstellar object. For context, the trajectories of planets and most comets are elliptical, looping around the sun in closed paths. But 3I Atlas's path is a straight line, bent only briefly by the sun's gravitational field, before it vanishes into the interstellar abyss. The hyperbolic excess velocity of 3I Atlas, 58 kilometers per second, is a critical clue to its origin. This speed, the velocity it would retain, even if the sun's gravity ceased to act upon it, places it among the fastest interstellar visitors ever observed. For comparison, 1I Oumuamua, the first interstellar object discovered in 2017, had a hyperbolic excess velocity of 26 kilometers per second, while 2I Borisov, identified in 2019, traveled at 32 kilometers per second. 3I Atlas's velocity suggests it came from a region of the galaxy where stars move at higher speeds relative to the sun, possibly the thick disk, a stellar population that orbits the Milky Way in a tilted, more chaotic pattern than the thin disk where our solar system resides. To understand how 3I Atlas reached the solar system, astronomers reconstructed its journey backward in time. Tracing its trajectory reveals that it originated from the direction of the galactic center, near the constellation Sagittarius. This origin is particularly intriguing because it lies in the southern celestial hemisphere, a region where interstellar object detections are rarer due to the dense star fields and interstellar dust that obscure faint objects. The fact that 3I Atlas was discovered at all is a testament to the power of modern astronomy, with surveys like Atlas and the Zwicky Transient Facility scanning the skies with unprecedented precision. As 3I Atlas approached the inner solar system, its interaction with the sun became a spectacle of cosmic chemistry. The sun's radiation, intense even at a distance of 4.5 astronomical units (AU), began to warm the comet's nucleus. This heating triggered the sublimation of volatile ices, primarily carbon dioxide, but also water, carbon monoxide, and traces of other compounds, creating a glowing coma and a tail of dust and gas. The James Webb Space Telescope, with its infrared vision, revealed that 3I Atlas's coma is unusually rich in carbon dioxide, a composition distinct from most solar system comets. This anomaly hints at a formation history unlike anything in our own backyard, perhaps in a protoplanetary disk where CO2 condensed at much colder temperatures than those found in the outer solar system. The comet's closest approach to the Sun will occur on 29 October 2025, at a distance of 1.36 AU, between the orbits of Earth and Mars. At this perihelion, 3I Atlas will be moving at a staggering 68 kilometers per second, its nucleus subjected to intense solar radiation. Observations during this phase will provide crucial insights into its stability. Will it fragment under the stress of rapid heating, as 2I Borisov did? Or will it endure, shedding gas and dust in a steady, graceful dance? The answers lie in the data collected by telescopes here on Earth and in space, as scientists piece together the story of a traveler from another world. The composition of 3I Atlas is a puzzle that offers tantalizing clues about its origins. Spectroscopic analysis by the James Webb Space Telescope and the SPHEREX mission have revealed a coma dominated by carbon dioxide, with lesser amounts of water ice, carbon monoxide, and carbonyl sulfide. This CO2-rich profile is strikingly different from solar system comets, which typically exhibit higher ratios of water to CO2. The presence of heavy isotopes of carbon, such as carbon-13, further complicates the picture. Isotopic ratios can serve as fingerprints of the conditions under which a comet formed, and the elevated levels of 1,4C in 3I Atlas suggest a history of prolonged exposure to cosmic radiation or a formation environment with unique chemical processes. One of the most intriguing aspects of 3I Atlas is its age. If it indeed originates from the Milky Way's thick disk, it could be at least 7 billion years old, far older than the solar system itself. The thick disk, a region populated by ancient stars, is thought to contain material from the early days of the galaxy. Amper's comet, this old, would have witnessed the birth and death of countless stars, surviving the violent upheavals of galactic evolution. Such an age raises profound questions. Could 3I Atlas have formed in a protoplanetary disk around a long-dead star? Has it endured collisions with other interstellar objects, its nucleus scarred by eons of cosmic travel? And what does its survival say about the resilience of cometary bodies in the harsh interstellar medium? The origins of 3I Atlas's parent star remain elusive. While its trajectory provides a general direction, the comet's journey through the galaxy has erased any direct link to its birthplace. However, the chemical composition of its coma offers indirect clues. The abundance of CO2 implies that 3I Atlas formed beyond the CO2 frost line in its home system, a region where temperatures are low enough for carbon dioxide to condense into ice. This suggests a parent star with a relatively cool protoplanetary disk, perhaps a red dwarf or a star with a lower metallicity than the Sun. The presence of nickel and cyanide in the coma, detected by the Very Large Telescope, further supports the idea of a chemically diverse formation environment, where complex organic molecules and metals coexisted. Yet, for all its revelations, 3I Atlas also raises questions that defy easy answers. Why is its coma so rich in CO2, while water remains a minor component? What mechanisms prevent the sublimation of water ice from dominating its activity? As is typical in solar system Comet, could 3I Atlas's unusual composition be the result of a unique evolutionary path, shaped by interactions with stellar winds or interstellar clouds? These mysteries underscore the importance of continued observation, as the comet's behavior during its closest approach to the Sun may yield further insights. Perhaps the most profound aspect of 3I Atlas is its role as a messenger from the depths of the galaxy. Every molecule it releases, every grain of dust it sheds, carries the imprint of a distant stellar system. By studying these fragments, we gain a window into the diversity of planetary formation processes across the Milky Way. Are comets like 3I Atlas common in other star systems? Do they play a role in distributing the building blocks of life across the galaxy? The answers may lie in the data collected during the comet's brief passage through the inner solar system, a fleeting opportunity to glimpse the chemistry of a world light years away. As 3I Atlas continues its journey through the inner solar system, its story is far from over. The data gathered by telescopes here on Earth and in space will keep scientists busy for years, unraveling the threads of its interstellar heritage. Yet, even as we catalog its chemical composition and map its trajectory, we are left with a humbling realization. This comet is a transient visitor, a ghostly whisper from a distant corner of the galaxy. Its path is predetermined, its fate sealed in the equations of physics. But what if humanity could do more than observe? What if we could reach out, not just with our instruments, but with our ingenuity, to meet this traveler on its journey? The challenges of intercepting 3I Atlas are immense. Any spacecraft launched from Earth after its discovery would require a delta V of at least 24 kilometers per second, an impossible feat with current propulsion technologies. Even a mission launched from Mars, as some studies suggest, would demand a level of coordination and engineering prowess that remains beyond our grasp. And yet, the dream of intercepting an interstellar object is not merely a fantasy. It is a call to push the boundaries of what is possible, to imagine missions that could one day bridge the vast gulfs between stars. In the coming decades, advances in propulsion, whether through nuclear thermal engines, solar sails, or even speculative concepts like antimatter drives, could make such missions viable. The lessons learned from 3I Atlas, from its composition to its trajectory, will inform the design of future probes. Perhaps one day, a spacecraft will be dispatched to meet an interstellar object, not as a passive observer, but as an active participant in the exchange of cosmic knowledge. Until then, we watch and wonder, our telescopes trained on the heavens, hoping to catch another glimpse of the universe's endless starry expanse. This script weaves scientific detail with a sense of cosmic wonder, inviting readers to contemplate humanity's place in the universe, while grounding the narrative in the real-world discoveries of 3I Atlas. Each section builds on the last, transitioning naturally from the mechanics of the comet's journey to the philosophical implications of its existence. In the vast, infinite expanse of the cosmos, where galaxies swirl like celestial dancers and stars are born from the remnants of ancient explosions, the universe has always whispered secrets to those who dare to listen. Among these whispers are the rare interstellar travelers, objects ejected from distant stellar systems, hurtling through the void like messengers from forgotten worlds. These cosmic wanderers, though fleeting in their visits to our solar system, carry with them the stories of their origins, encoded in their trajectories, compositions, and the scars of their journeys. One such traveler, 3I Atlas, emerged from the darkness on 1 July 2025, a comet born not in our corner of the galaxy, but in the distant shadowed depths of interstellar space. 3I Atlas is the third confirmed interstellar object to traverse our neighborhood, following the enigmatic 1I Oumuamua and the more familiar 2I Borisov. Its arrival marked another milestone in humanity's quest to understand the universe, a reminder that we are not alone in the cosmic tapestry, but rather threads woven into a grander pattern. The discovery of 3I Atlas ignited a surge of scientific curiosity as astronomers raced to unravel its mysteries. Where did it come from? What secrets does it hold about the birth of stars and planetary systems? And what does its journey tell us about the dynamic, interconnected nature of the Milky Way? As the comet approached the Sun, its icy nucleus, cloaked in a shimmering coma of gas and dust, began to react to the solar warmth. Jets of vapor and particles erupted from its surface, painting a transient portrait of activity against the backdrop of the solar system. To observers on Earth, 3I Atlas was a faint smudge in the night sky, a ghostly apparition that demanded patience and precision to track, yet its significance transcended its visual subtlety. Every observation, every spectral signature, and every calculation brought us closer to answering profound questions about our place in the cosmos. This script delves into the story of 3I Atlas, tracing its discovery, decoding its nature, and contemplating the implications of its existence. Through the lens of science and imagination, we embark on a journey, not just to understand a single comet, but to glimpse the vast interconnected web of life and matter that binds the universe together. The tale of 3I Atlas begins with a telescope nestled in the arid skies of Chile, where the asteroid terrestrial impact last alert system, ATLAS, scans the heavens for potential threats. On 1 July 2025, the system captured a faint moving object in the constellation of Sagittarius, near the galactic plane. At first glance, it seemed unremarkable, a speck of light among countless others. But as astronomers refined its orbit, a startling truth emerged. The object was moving far too fast to be bound to the sun. Its trajectory was hyperbolic, a path that would carry it out of the solar system forever. What followed was a frenzied dance of observations. Professional and amateur astronomers alike turned their instruments toward 3I Atlas, piecing together its story from the fragments of light it scattered. The Zwicky Transient Facility, the Hubble Space Telescope, and the James Webb Space Telescope joined forces, their combined gaze revealing a comet unlike any seen before. By the time the Minor Planet Center officially designated it as 3I Atlas, a wealth of data had already been gathered. The comet's nucleus, shrouded in a coma of gas and dust, was estimated to be less than a kilometer in diameter, a tiny world by cosmic standards, yet rich in volatile compounds. What sets 3I Atlas apart is its chemical fingerprint. Spectroscopic analysis unveiled a coma unusually rich in carbon dioxide, with traces of water ice, carbon monoxide, and carbonyl sulfide. These molecules are the building blocks of life, forged in the cold crucibles of interstellar space. The presence of cyanide and atomic nickel, detected by the Very Large Telescope, added another layer of intrigue. Such elements are common in comets, yet their abundance in 3I Atlas hinted at a history shaped by the violent processes of its parent star system. The comet's journey through the solar system is a testament to its resilience. Discovered at a distance of 4.5 astronomical units, AU from the Sun, 3I Atlas will reach perihelion, the point of closest approach, on 29 October 2025, at a mere 1.36 AU. This places it between the orbits of Earth and Mars, a region where the Sun's energy will accelerate its activity. Yet despite its proximity, 3I Atlas poses no danger to our planet. Its hyperbolic excess velocity of 58 kilometers per second ensures that it will escape the Sun's gravitational grasp, continuing its voyage into the unknown. The origin of 3I Atlas remains a puzzle. Tracing its trajectory backward through the Milky Way, astronomers found that it hailed from the direction of the galactic center, near the boundary of the thin and thick disks. These stellar populations differ in age and composition, with the thick disk hosting stars billions of years older than the Sun. If 3I Atlas indeed originates from the thick disk, it could be 7 billion years old, far older than the solar system itself. Such an age would make it a relic of the Milky Way's earliest days, a cosmic fossil carrying the memory of a long-lost planetary system. Yet the comet's true parent star remains elusive. Over billions of years, 3I Atlas has likely drifted through interstellar space, its path altered by encounters with stars and nebulae. While its origin star cannot be identified, the comet's composition offers clues. The abundance of carbon dioxide suggests it formed beyond the CO2 frost line in its home system, a region where temperatures are low enough for ices to condense. This implies that 3I Atlas was once part of a protoplanetary disk, a swirling nursery of gas and dust that gave rise to planets. At some point, gravitational interactions with a giant planet or passing star ejected it into the void, setting it on a journey that would eventually bring it to our doorstep. As 3I Atlas draws closer to the Sun, its transformation becomes a spectacle of cosmic alchemy. The solar wind and radiation begin to peel away layers of its icy shell, releasing plumes of gas and dust that form a glowing coma. This ethereal cloud, spanning tens of thousands of kilometers, is a mirror of the comet's internal structure, reflecting the volatile compounds trapped within its nucleus. The reddish hue of the coma, observed by telescopes on Earth and in space, hints at the presence of complex organic molecules, carbon-rich compounds that may have played a role in the emergence of life on Earth. One of the most striking features of 3I Atlas is its CO2-rich coma. While water ice dominates the activity of most comets, 3I Atlas's sublimation of carbon dioxide creates a unique chemical profile. This anomaly has sparked debates among scientists. Does it reflect the conditions of its parent star's protoplanetary disk, or does it indicate a process of selective volatilization as the comet traverses the galaxy? The James Webb Space Telescope's observations have provided critical insights, detecting not only CO2 but also isotopes of carbon-13, offering a glimpse into the nuclear processes that shaped its birthplace. The comet's interaction with the Sun is a delicate balance of destruction and creation. As it approaches perihelion, the intense solar heating accelerates its outgassing, potentially triggering outbursts or even fragmentation. Yet, 3I Atlas appears resilient, its activity proceeding steadily, without the dramatic disintegration seen in 2I Borisov. This stability raises questions about the strength of its nucleus and the distribution of volatile materials within. Are the ices buried deep beneath a protective crust, or are they evenly distributed, allowing for gradual release? The answers lie in the data streaming from observatories around the globe, each observation adding another piece to the puzzle. The comet's rotation, though difficult to measure due to its dusty coma, has been estimated at approximately 16 hours. This relatively slow spin suggests a nucleus shaped by millennia of collisions and gravitational perturbations, its irregular form a testament to the chaotic forces that govern the cosmos. As it spins, the interplay of sunlight and shadow across its surface creates subtle variations in brightness, a silent ballet of ice and rock. These fluctuations, captured by the Hubble Space Telescope, offer indirect clues about the comet's orientation and the distribution of its volatile reservoirs. Even as 3I Atlas nears its closest approach to the Sun, the scientific community remains vigilant. The Vera C. Rubin Observatory, still in its commissioning phase, has already contributed valuable data, tracking the growth of the coma and refining estimates of the nucleus's size. Meanwhile, the Transiting Exoplanet Survey satellite TESS has revealed that the comet's activity began as early as May 2025, when it was 6.4 AU from the Sun. This early activation suggests that 3I Atlas harbors volatile ices beyond water, such as carbon monoxide or methane, which can sublimate at lower temperatures. Such findings challenge our understanding of cometary behavior, pushing the boundaries of what we know about these ancient wanderers. Yet the most profound mystery of 3I Atlas lies in its origin. If it is indeed a relic of the Milky Way's thick disk, it predates the solar system by billions of years. In that case, it carries the imprint of a vastly different galactic environment, one where stars were younger, more metal-poor, and the chemistry of the interstellar medium was starkly different. The detection of nickel vapor and cyanide in its coma adds another layer of complexity, suggesting that its parent star system may have hosted unique chemical processes. Could such conditions have fostered the precursors of life, or do they simply reflect the raw materials of a primordial era? These questions linger like the comet's fading tail, urging us to look deeper into the cosmos. As 3I Atlas departs the solar system, its legacy endures. The data it leaves behind is a treasure trove for generations of scientists, a window into the distant past, and a beacon for the future of interstellar exploration. Yet, its passage also stirs a more profound reflection. What does it mean to witness a visitor from another star system? For millennia, humans have gazed at the night sky, searching for meaning in the stars. Now we stand on the threshold of a new era, one where we can not only observe, but engage with the cosmos in ways our ancestors could scarcely imagine. The challenges of reaching 3I Atlas underscore the immense hurdles of interstellar travel. Launching a probe to intercept it would require velocities beyond our current capabilities, a daunting task that highlights the ingenuity and perseverance required to bridge the gap between Earth and the stars. Yet the possibility of a Mars-launched mission, leveraging the red planet as a stepping stone, offers a glimmer of hope. It reminds us that the universe, vast and indifferent, is not beyond our reach, if we dare to dream and innovate. But 3I Atlas is more than a scientific curiosity. It is a symbol of our shared destiny as explorers, a reminder that the cosmos is not a void, but a tapestry of connections. The same forces that sculpted 3I Atlas's icy nucleus also forged the planets of our solar system. The same elements that now drift in its coma once cycled through ancient stars, their light illuminating the dark corners of the galaxy. In studying this comet, we are not merely observing an interstellar traveler, we are uncovering the threads that bind us to the universe itself. As 3I Atlas vanishes into the depths of space, its story becomes part of the human narrative. It challenges us to think beyond our immediate surroundings, to consider the vast interconnected web of life and matter that stretches across the cosmos. In its wake, it leaves a question that echoes through time. What other wonders await us in the stars? The answer lies not in the comet itself, but in the endless journey of discovery that defines our species. In the vast, silent expanse of the cosmos, where stars are born and die in cycles older than memory, the universe whispers its secrets through fleeting visitors. Among these transient messengers, 3I Atlas stands as a singular enigma, a comet born not in the familiar cradle of our solar system, but in the distant ancient dark of interstellar space. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas, in Chile, this object arrived at the doorstep of the Sun like a ghost from another epoch, its path carved by velocities that defy the gravitational bonds of our star. 3I Atlas is no ordinary comet. It is the third interstellar object confirmed to have traversed our cosmic neighborhood, following the mysterious cigar-shaped 1I Oumuamua Meikli 17 and the more familiar 2I Borisov Meikli 2019. Yet, unlike its predecessors, 3I Atlas carries a burden of age. It may have journeyed for billions of years, its origins tied to the Milky Way's thick disk, a realm of stars older than the solar system itself. As it hurtles through the inner solar system, its icy nucleus releasing clouds of gas and dust, 3I Atlas offers a rare glimpse into the primordial chemistry of distant star systems. It is a relic of a forgotten era, a traveler that bridges the chasm between worlds. But why does 3I Atlas matter? Beyond its scientific intrigue, it stirs something deeper, a recognition of our smallness in the grand tapestry of the cosmos. In its silent passage, we see the interconnectedness of galaxies, the ceaseless exchange of material across light years, and the humbling truth that we are not alone in the universe's story. To study 3I Atlas is to peer into the past of other stars, to trace the echoes of creation and destruction that shape the fabric of existence. And as it departs, leaving behind a trail of carbon dioxide, cyanide, and nickel, we are left with a question: what else lies hidden in the void, waiting to be discovered? To comprehend 3I Atlas is to unravel the threads of its journey, a journey governed by the immutable laws of physics and the chaotic dance of celestial mechanics. The comet's hyperbolic trajectory, defined by an orbital eccentricity of 6.141, is a stark declaration of its interstellar origin. Unlike the elliptical paths of native comets, which are tethered to the sun's gravity, 3I Atlas's path is a straight line, bent only briefly by the sun's pull before it escapes into the void. Its hyperbolic excess velocity of 58 kilometers per second, 36 mph, is a testament to its speed. It arrived here at nearly double the velocity of 2I Borisov and over twice that of 1I Oumuamua. Such speed is impossible for an object born in the solar system. No known gravitational interaction within our planetary neighborhood could accelerate 3I Atlas to such a velocity. Instead, its motion is a signature of its true origin, a star system far beyond the reach of the sun's influence. Yet, 3I Atlas is not merely a speeding rock. It is a dynamic world, its nucleus cloaked in a coma of gas and dust. The sun's heat sublimates volatile ices, primarily carbon dioxide, water, and carbon monoxide from its surface, creating a luminous envelope that stretches thousands of kilometers. Observations by the James Webb Space Telescope, JWST, revealed that 3I Atlas's coma is unusually rich in CO2, with a mixing ratio to water 8 times higher than most solar system comets. This anomaly hints at its formation in a frigid, distant realm, where CO2 could freeze into solid grains. Meanwhile, the detection of cyanide gas and atomic nickel vapor by the Very Large Telescope adds to the comet's mystique. These elements, typically associated with organic chemistry and metallic compounds, suggest a complex internal composition shaped by the crucibles of its parent star's protoplanetary disk. The comet's nucleus remains shrouded in mystery. Hubble Space Telescope images estimate its diameter between 0.32 and 5.6 kilometers, though the true size is likely at the lower end. Obscured by the brightness of the coma, theoretical models suggest that 3I Atlas's nucleus is rocky and porous, its surface pitted with jets of gas and dust. As it approaches perihelion on 29 October 2025, its activity will intensify, potentially triggering outbursts or even fragmentation, events that could scatter its secrets across the solar system. Yet for now, 3I Atlas remains a stable traveler, its cometary activity a delicate balance between the sun's warming embrace and the cold legacy of its interstellar birthplace. What sets 3I Atlas apart from its solar system kin is its chemical fingerprint. Unlike native comets, which bear the isotopic signatures of the early solar nebula, 3I Atlas's CO2 contains a higher proportion of the heavier isotope carbon-13. This deviation suggests a different stellar nursery, one where nuclear fusion and supernova remnants alter the elemental ratios. Moreover, the absence of certain compounds such as carbon chain molecules like C2 and C3 points to a unique evolutionary history, perhaps shaped by intense radiation or prolonged exposure to the galactic magnetic field. Even its trajectory tells a story, tracing 3I Atlas's path backward through the galaxy. Astronomers find it originated in the direction of the Milky Way's thick disk, a region dominated by ancient stars. If it indeed hails from this population, its age could exceed 7 billion years, making it older than the solar system itself. Such a timeline implies that 3I Atlas formed in an era when the galaxy was younger, its stars closer and its disks more turbulent. Perhaps it was ejected from its home system during a violent planetary migration, or a stellar encounter, cast adrift to wander the interstellar void for eons. In every particle of gas and grain, 3I Atlas carries a narrative of cosmic recycling, the transformation of stellar debris into new worlds. Its journey is not an anomaly, but a reminder that the universe is a web of interconnected systems, where the materials of one star seed the birth of another. The arrival of 3I Atlas forces us to confront a profound truth. Our solar system is not an island. It is part of a vast interwoven galactic ecosystem, where comets, asteroids, and rogue objects serve as vectors for the exchange of matter and energy. The study of interstellar comets like 3I Atlas challenges the traditional boundaries between home and foreign, revealing that the building blocks of life and the raw materials of planetary systems are not confined to any single star. Instead, they are shared commodities in the cosmic economy, carried across light years by the tides of gravity and time. Consider the implications for astrobiology. Comets are known to carry organic molecules, including amino acids and nucleobases, the precursors to life. If 3I Atlas shares this trait, it could imply that the seeds of biology are not unique to the solar system, but are distributed throughout the galaxy. The Milky Way's thick disk, from which 3I Atlas may originate, is a repository of ancient stellar populations. If comets from this region regularly traverse interstellar space, they could act as cosmic couriers, delivering organic compounds to nascent planetary systems. In this scenario, life's ingredients are not the product of chance but of a universal process, one that blurs the lines between planets and stars, between individual systems and the collective whole. The age of 3I Atlas, potentially exceeding 7 billion years, adds another layer of intrigue. If it predates the solar system by tens of millions of years, it could have originated in a stellar system that no longer exists, its host star long dead or scattered by galactic tides. This raises the tantalizing possibility that 3I Atlas carries memories of a civilization that once thrived in the Milky Way's past. While the speculation about extraterrestrial spacecraft remains controversial and largely dismissed by the scientific community, the mere existence of such a hypothesis underscores the limits of our current understanding. Could advanced civilizations have harnessed comets as vessels or probes? Might their remnants, like 3I Atlas, drift silently through the void, waiting to be rediscovered? Even without invoking intelligence, 3I Atlas embodies the concept of panspermia, the idea that life's building blocks, or even microbial organisms, could hitchhike on interstellar objects. If comets like 3I Atlas routinely traverse the galaxy, they might deposit organic material on planets where conditions allow for chemical evolution. Earth itself may owe its biochemistry to such a delivery, its earliest oceans enriched by the detritus of distant stars. In this framework, 3I Atlas is not just a visitor, it is a participant in the cosmic cycle of creation, a bridge between the death of one star system and the birth of another. Yet, the study of 3I Atlas also highlights the fragility of knowledge. Much of what we learn about this comet depends on fleeting observations, as it remains beyond the reach of spacecraft. Its interior composition, the precise nature of its nucleus, and the mechanisms driving its activity are all inferred from remote sensing. This limitation mirrors humanity's broader struggle to understand the universe. We are forever observers at the edge of the unknown, piecing together truths from glimpses and shadows. The James Webb Space Telescope's detection of CO2 and the Hubble's imaging of its coma are testaments to our ingenuity, but they also remind us of how much remains unseen. Perhaps the greatest lesson of 3I Atlas is its role as a mirror. It reflects our curiosity, our hunger to connect the dots between stars, and our humility in the face of the infinite. When we gaze at 3I Atlas, we see not just a comet, but a symbol of our shared cosmic heritage. It is a reminder that the atoms in our bodies, the air we breathe, and the very ground beneath our feet are forged in the crucibles of stars long gone. The universe is not a void, it is a symphony, and every interstellar traveler is a note in its eternal song. As 3I Atlas reaches its perihelion and begins its escape from the solar system, it leaves behind more than a trail of gas and dust. It leaves a question mark, a call to action, and a sense of wonder that transcends the boundaries of science and philosophy. Its journey, though brief in human terms, is a microcosm of the universe's grandeur, a fleeting encounter between systems, a whisper of the past carried forward into the future. For now, 3I Atlas fades into the darkness, its light dimming as it retreats beyond the orbits of Mars and Jupiter. By the time it clears the outer planets, it will be invisible to even the most powerful telescopes, its story preserved only in data and speculation. Yet, its legacy endures. The data collected by Hubble, JWST, and ground-based observatories will fuel decades of research, unraveling the mysteries of interstellar comets and the processes that shape them. Future missions, armed with better instruments and bolder ambitions, may one day intercept such objects in real time, analyzing their nuclei in unprecedented detail. But beyond the science, 3I Atlas compels us to reimagine our place in the cosmos. It is a reminder that the universe is not static or hostile, but alive with movement and exchange. Every star is a node in a vast network, every comet a thread in the tapestry of cosmic history. As 3I Atlas disappears into the void, it carries with it the promise of discovery, the assurance that the universe is full of stories waiting to be told, and that we are but one chapter in its endless saga. And so, we turn our eyes to the skies, not with fear, but with hope. For in the silence between the stars, there is music. In the darkness, there is light. And in every stranger that visits from the depths of space, there is a lesson: to listen, to wonder, and to dream. In the vast, silent expanse of the cosmos, where stars burn like distant beacons and galaxies swirl in eternal spirals, a single traveler has ignited the imagination of humanity. 3I Atlas, the third interstellar object to grace our solar system, is no ordinary comet. It is a relic of another star's birth, a wanderer born in the cradle of a distant stellar nursery, now hurtling through the void on a collision course with our cosmic neighborhood. Discovered in the summer of 2025 by the Atlas Survey Telescope in Chile, this icy vagabond carries with it secrets of a universe far older and stranger than we can comprehend. Its arrival is not merely an astronomical event, but a profound reminder of our place in an infinite tapestry of matter and energy, where the boundaries between the familiar and the alien blur. 3I Atlas's journey began long before its detection, traversing the galactic abyss for billions of years. It is a time capsule from an era predating the birth of our solar system, a fragment of a world that no longer exists. Its hyperbolic trajectory, a path unshackled by the gravitational pull of the sun, marks it as a visitor from the depths of interstellar space. Yet despite its alien origins, 3I Atlas behaves like the comets we know, its nucleus encased in a coma of gas and dust, its surface erupting in bursts of volatile ices as it dances with the sun's warmth. In this paradox lies the essence of its wonder. It is both foreign and familiar, a bridge between the known and the unknown. As scientists and stargazers alike turn their eyes to the sky, 3I Atlas invites us to contemplate the interconnectedness of the cosmos. It whispers of star systems we've never seen, of protoplanetary disks where worlds coalesced from swirling clouds of gas and dust, and of the ceaseless dance of celestial bodies across the void. To study this comet is to trace the threads of a cosmic web, to glimpse the raw ingredients of life and the forces that shape the universe. In its fleeting passage, 3I Atlas offers a rare opportunity to peer beyond the boundaries of our own stellar home, to ask what else lies in the darkness, and to marvel at the ingenuity of nature in crafting such enigmatic wonders. 3I Atlas's trajectory is a testament to its interstellar heritage. Unlike the comets that originate in the Kuiper belt or the distant Oort cloud, this object does not belong to the solar system. Its path is defined by a hyperbolic orbit, a mathematical curve so extreme that it ensures the comet will never return. With an orbital eccentricity of 6.141, the highest recorded among interstellar visitors, 3I Atlas moves through the inner solar system at a blistering 58 kilometers per second, a speed so great that it defies the sun's gravitational grasp. This velocity, known as the hyperbolic excess speed (VITEC), is the true signature of its alien origin. To achieve such a velocity, 3I Atlas must have been ejected from its parent star system, flung into the void by gravitational interactions with planets or passing stars. As 3I Atlas approaches the Sun, it undergoes a transformation as dramatic as its origin story. The solar radiation warms its icy nucleus, triggering a process called sublimation, in which frozen volatiles like water, carbon dioxide, and carbon monoxide transition directly from solid to gas. This outgassing creates a luminous coma, a cloud of gas and dust that envelops the nucleus like a ghostly halo. The coma expands outward, forming a tail that stretches millions of kilometers into space, driven by the solar wind and radiation pressure. Observations by the Hubble Space Telescope reveal that 3I Atlas's coma is unusually rich in carbon dioxide, a compound that dominates its volatile inventory. This is a stark contrast to most solar system comets, which are primarily composed of water ice. The presence of CO2 suggests that 3I Atlas formed in the frigid outer reaches of its parent star's protoplanetary disk, beyond the CO2 frost line where temperatures are low enough for this molecule to condense into solid form. The comet's composition is further illuminated by spectral analysis from the James Webb Space Telescope, JWST, and the THEREX mission. These instruments have detected traces of water ice, carbon monoxide, and carbonyl sulfide, OCS, in its coma, alongside the enigmatic presence of cyanide gas and atomic nickel vapor. The latter discovery is particularly intriguing, as nickel emission has been observed in comets before, but its absence of iron vapor, a common companion, raises questions about the chemical processes at play. Theories propose that nickel-containing organic compounds, such as nickel tetracarbonyl, may decompose under the harsh conditions of interstellar travel, releasing atomic nickel into the coma. Meanwhile, the scarcity of carbon chain compounds like C2 and C3 in 3I Atlas's coma sets it apart from many solar system comets, hinting at a unique evolutionary history shaped by its interstellar journey. Perhaps the most astonishing aspect of 3I Atlas's story is its age. By tracing its trajectory backward in time, astronomers estimate that it originated from the Milky Way's thick disk, a stellar population that includes some of the galaxy's oldest stars. If this hypothesis holds, 3I Atlas could be as ancient as 7.6 billion years, making it older than the solar system itself. Such an age implies that the comet formed in a star system that no longer exists, its parent star long since consumed by the cycle of stellar death and rebirth. The thick disk's low metallicity, its scarcity of elements heavier than helium, further supports this idea, suggesting that 3I Atlas's parent star was born in a primordial environment, where heavy elements were still rare. This places the comet in a category of objects that predate the formation of our own planetary neighborhood, offering a glimpse into the early stages of galactic evolution. Yet, for all its scientific intrigue, 3I Atlas remains a puzzle. Its nucleus, obscured by a veil of dust, eludes precise measurement, with estimates ranging from 0.32 to 5.6 kilometers in diameter. The discrepancy arises from the challenge of disentangling the nucleus's light from the coma's glow, a task complicated by the comet's dynamic activity. As 3I Atlas draws closer to the Sun, its outgassing intensifies, and its coma swells, threatening to overwhelm the faint signal of its core. This uncertainty underscores the delicate balance between observation and inference in astrophysics, where every piece of data is a thread in the intricate tapestry of cosmic truth. The study of 3I Atlas has transcended the realm of pure science, becoming a crucible for interdisciplinary inquiry and philosophical reflection. Its discovery has reignited debates about the origins of comets, the potential for interstellar panspermia, the transfer of organic material between star systems, and the limits of human knowledge. For planetary scientists, the comet represents a unique laboratory for testing theories of volatile distribution and comet formation in diverse stellar environments. The dominance of CO2 in its coma, for instance, challenges existing models of cometary chemistry, which assume that water ice is the primary volatile in such objects. This anomaly has spurred investigations into the conditions necessary for CO2 to dominate, with researchers considering scenarios where 3I Atlas's parent star hosted a CO2-rich protoplanetary disk, or where prolonged exposure to cosmic rays altered its composition. Beyond the scientific community, 3I Atlas has captured the public imagination, serving as a metaphor for the unknown. Its interstellar origin evokes a sense of awe and humility, reminding us that we are but one species among countless others, adrift on a single planet in an ocean of stars. The comet's trajectory, which aligns unexpectedly with the solar system's ecliptic plane, has even prompted speculative discussions about its possible artificial nature. In July 2025, astrophysicist Avi Loeb and colleagues proposed that 3I Atlas might be an extraterrestrial spacecraft, citing its anomalous size, chemical profile, and trajectory. While this hypothesis has been met with skepticism and criticism from the broader astronomical community, it highlights the enduring human fascination with the possibility of intelligent life beyond Earth. The debate has sparked a broader conversation about the criteria for distinguishing natural phenomena from engineered ones, emphasizing the need for rigorous evidence and open-mindedness in the face of the unknown. At the heart of this discourse lies a fundamental question: how do we define natural? In a universe that is both boundless and enigmatic, 3I Atlas challenges our assumptions by existing in a liminal space between the familiar and the alien. Its carbon dioxide-rich coma, its ancient age, and its interstellar provenance defy easy categorization, forcing scientists to confront the limitations of their frameworks. This uncertainty is not a failure of science, but a testament to its vitality, a reminder that the pursuit of knowledge is as much about asking the right questions as it is about finding answers. The comet's journey also underscores the power of collaboration in modern astronomy. From the initial detection by Atlas to the follow-up observations by the Hubble, JWST, and ground-based telescopes like the Very Large Telescope, 3I Atlas has been a collective effort spanning continents and disciplines. Volunteers, amateur astronomers, and professionals have contributed observations that refined the comet's trajectory and revealed its secrets. This global network exemplifies the interconnectedness of the scientific endeavor, where data flows freely across borders and cultures to illuminate the mysteries of the cosmos. Yet for all its scientific value, 3I Atlas is a fleeting guest. By late 2025, it will have passed perihelion and begun its return to the interstellar void, its brilliance fading as it retreats into the darkness, but its legacy will endure. The data it leaves behind will fuel generations of research, inspiring new models of comet formation, new instruments for probing the cosmos, and new questions about our place in the universe. And perhaps one day, another interstellar traveler will arrive, carrying its own story, its own riddles, and its own promise of wonder. As 3I Atlas fades from view, its journey serves as a poignant reminder of the impermanence of all things, even the grandest of cosmic phenomena, like a shooting star streaking across the sky. It appears for a brief moment, igniting our imaginations before slipping back into the vastness from which it came. Yet, in that moment, it has left an indelible mark on our understanding of the universe. It has reminded us that the cosmos is not a static realm, but a dynamic, ever-changing expanse, where objects are born, collide, and drift apart in an endless waltz of creation and destruction. The study of 3I Atlas is not an endpoint, but a beginning. It has opened new avenues of inquiry, from the chemistry of interstellar comets to the mechanics of their ejection from star systems. Future missions, equipped with next-generation telescopes and spectrometers, will build upon this foundation, seeking to unravel the mysteries of other interstellar visitors and their origins. Perhaps one day, a probe will intercept an interstellar object, collecting samples that will revolutionize our understanding of the building blocks of life. Until then, we are left with the wonder of 3I Atlas, a comet that bridged the chasm between stars and brought the universe closer to our doorstep. In the quiet aftermath of its departure, we are left to ponder the questions it has raised. What other travelers lurk in the dark, waiting to be discovered? What stories do they carry, and what truths will they reveal? The answers lie not in the heavens themselves, but in our willingness to seek them, to look up with curiosity and humility, and to embrace the unknown as a source of inspiration rather than fear. For in the act of searching, we find not only the universe but ourselves, small, fleeting, and yet infinitely connected to the great cosmic dance.